So is it audible? 2 मिनट के लिए इसका वॉल्यूम कर दो. There are some technical issues going on. Just give us few minutes. Okay. Let me know. Hello, bacho. Let me know if you have also started the lecture. Let's start with the first topic, that is RMP, AP and EC coupling, because it is fine on my side. Very good evening all of you. We are going to start with the resting membrane potential. Then we are going to move on to some action, and then we are going to convert that action into contraction. So first of all, from resting to we are going to go to the action, and then EC coupling, that is excitation, contraction, coupling. And trust me, in all university exam, this question is must. Either it is going to come into your terms or profs or centups, but it is going to be there. And trust me, in prof, one of these questions are going to be there from the nerve muscle physiology. Okay, so either they can ask you about the conduction, they can ask you about action potential of different structures, or they can ask you about the excitation, contraction, coupling. I'm going to give you some homework questions also, okay, so that you can just go through them and just understand, or just make a point in your head that if this question comes for these many marks, I'm going to write these points. Okay, so enlist the points so that one day before the exam you have the points ready with you. You just have to go through these points, that if this question comes, I'm going to write these things, I'm going to make this type of charts, and I'm going to write the paper very nicely and smartly. Okay, so let's start with the first thing, that is the cell membrane. Okay, and we know that we don't have cell membranes like other doors. Okay, we do have cell membrane which shows partiality. Now what I mean by that, see over here, the cell membrane in our cell, these are what things? The cell membrane, CM means cell membrane, and the cell membranes are semi-permeable. They're not completely permeable, understand? Semi-permeable. What do you mean by semi? Semi means somewhere in the middle, right? That means half. So they are semi-permeable. That means they will allow some substances to come in and go out, and they won't allow some substances, right? So we have to, make the borders. Or for example, the AC is on right now. I do not want my AC's cool air to go outside and outside hot air to come inside the room, and that's why I have the walls. And similarly, the cells also do not want the exchange of various different things at all the time, so that's why they have the membrane. That's the boundary of the wall, isn't it? So that is the semi-permeability. Now remember, this is very important phenomena. Why? Because of whatever is happening in the cell, this is because of this property only. Okay, we are surviving because of this permeability property itself, right? So at the rest, what is going to happen? Let's see. This is semi-permeable. That means the cell membrane will allow some. That means the cell membrane allow some substances to pass through, and it won't allow the other substances, right? Pass through, and it won't allow, or it will not allow some other substances, let's write. So because of that, what is going to happen? There is going to be two different substances, or groups of two different substances are formed. What are the two different substances? That means the first group will be of the ions which can cross the cell membrane easily at rest, and if they can cross without the help of any carrier or protein or receptor, that means we do have diffusion over there, because it's a passive movement, isn't it? So please remember, if the ions are able to pass through in the rest, we are going to call them as diffusible ions, because they're not using any energy, they're not using any channels per se, they are just either leaking outside or coming inside or leaking inside, right? And that's why we are using the terminology diffusible over here, because the diffusion of those substances, it is allowed at the time of rest, right? So diffusible ions, the ions which can pass through, good evening Rahul, the ions which can pass through without the support of channel or any carrier protein, and that's why we are going to call them as diffusible ion. And at what time? We are not stimulated the cell yet, right? It is at rest. So what are the examples of such diffusible ions? There are two main examples. You cannot afford to forget it. That is, first one is potassium and the second one is chloride. Okay, that means all other charged particles or all other electrolytes, they cannot pass through the cell membrane at the time of rest, right? So these two ions are very, very, very important. Why? Because everything, the story behind all the RMP and AP, it is carry forwarded via this only property, that is the semi-permeability, right? So what are the other group, or what are the ions in the other group? That is non-diffusible ions. So they are going to be non-diffusible ions. So that means they are not permeable at the time of rest, isn't it? So if they are not permeable at the time of rest, they will be called as non-diffusible ions, right? And what are the example? Rest all will be non-diffusible. What are the examples? Sodium, calcium, then the bicarbonate. Not only that, we do have phosphates, proteins, so on and so forth. All of them are non-diffusible ions. That means they are not permeable at the time of rest. And we have to give the stimulus if you want these ions to pass through the membrane. Why? Because we have to give the stimulus, and the stimulus will open up some channels through which they are going to pass through the membrane. Otherwise, at the rest, this is not going to happen at all, right? So the cell is showing the partiality, and because of this, what is going to happen? See the example over here. There is going to be unequal distribution which is going to take place. What I mean by that? We know that the potassium is more inside the cell. I told you in the first lecture itself that the cell is a bag of potassium, and as we developed or evolved into the seawater, that's why outside of the cell, that means in the interstitial fluid and the extracellular fluid, we want salty type of environment. That means sodium and chloride that should be higher surrounding the cell, isn't it? So let's take the example of potassium, and I told you that the potassium is permeable at the time of rest also. So let's take an example that, let's say at the time of rest, the concentration of potassium ion inside is 140 and outside it is around 14 milliequivalent per liter. It's too high, but I'm just taking as an example over here. Now, at rest, they should be able to go out unless and until they balance each other, isn't it? So similar amount of ions that should be outside and inside, right? Then only their flux will stop. That means their movement should stop, isn't it? But that is not going to happen. Why? Because understand, yes, they are permeable at the time of rest, but they are not the only ions present in the body, right? Inside, what are the ions which are present? Yes, guys, what is the answer? Phosphates. Not only that, proteins are going to be there. And outside we do have sodium ion, chloride ion, and the calcium and everything outside. Right? Now understand what is going to happen because of these changes. That the potassium will start leaking outside. Okay? It is start leaking outside. That means it is the positively charged ion going outside the cell. It is going to cause hyperpolarization of the cell. Why? Because the RMP, resting polarity of all the cells, it is already negative and you are going more into negative. Why? Because your positively charged ion leaving the cell, right? As we do have somewhat stress will make us go in the hyperpolarization, we lose the motivation, we lose the inspiration. Same, our positive motivation go out of the window. Same, this is going to happen in the cell, that the potassium will start leaking outside. But at some point we know we have to hold on to the positive thoughts, right? So same over here. For that we do have phosphate and protein. Understand, there is chemical gradient which is forcing the potassium to go outside. Why? Because there is a lot of concentration difference, that is the gradient present between inside and outside of the cell. But electrical gradient is going to say otherwise. Why? Because we do not want to lose a lot of positively charged ion, otherwise the cell will become so much hyperpolarized that it cannot be stimulated any further. And these negatively charged ions, we know from the law of chemistry that the opposite electrolytes, they attract each other, and that's why the blue color arrow that I showed over here, that is because of the chemical gradient. But understand, when we talk about the electrical gradient, because of these negatively charged molecule, remember the proteins are also negatively charged, the main or major negatively charged ion inside the cell is going to be phosphate. Now understand what they are going to do. They are going to hold on to the potassium. They will not let much of the potassium to go out, right? So that to maintain the electrical balance. Now understand that the potassium outside and inside, it is still not equal, but whenever this concentration gradient and electrical gradient, they become equal and opposite, the potassium won't be able to move. So that's why what is going to happen? The potassium movement will be stopped, or we can say the flux will stop over there, and that's why the much of the potassium won't be able to leave the cell. And when we are going to measure the magnitude of potential difference, that will be called as your Nernst equation. But the potassium is not able to move out completely. For example, if I take another example, I'll share one easy example. Suppose there is X ion. This is a semi-permeable membrane. Let's say this is X ion, which is positively charged, and there are 100 molecules which are present inside, and outside only 10 molecules are present. Now in total we have 110. That means it should move. If it is completely permeable, then it is going to move out till the time it becomes 55 inside, 55 ions outside. But if I add some of the negative ions over here, let's say Y is the negatively charged ion, this is going to change. This equation is going to change. Now instead of 55 and 55 over here, that means instead of becoming equal both the side, because if I say, let's say there are 10 molecules over here extra, so the extra 10 molecules are going to stay inside. Okay, so rather than doing the math over here, let's understand that let's say 20 molecules are there, right? Instead of 55, it will remain 75 to 80 inside, right? Let's say 75 itself, and that means the 20 will be less outside. That means only 35 will be there outside. So they're not yet equal. The X ions inside the cell and X ions outside the cell, they are not equal, but the flux will stop over here, right? In this case, the flux will stop even before it becomes equal, right? That means the X ions won't move outside, and this happened because of non-diffusible cells, these non-diffusible ions or non-permeant ions. They will hold on to the permeant ions also. So there is going to be unequal distribution of all the ions for that matter, right? So this is known as, that means the non-permeant ions, they are affecting the permeant ion. This is known as Gibbs equilibrium. Okay, very easy. Gibbs equilibrium. There is an unequal distribution. Why? Because understand, there is an effect of, or let's say non-permeant ion, non-diffusible ion, change the or have the effect on the permeability. Non-diffusible ions have the effect on distribution of diffusible ions. Effect of diffusible ions, and that is called as Gibbs equilibrium. How to remember? It's a very easy trick. What is the easy trick? D, 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 isn't it? The effect of non-diffusible ion on the diffusible ion, that is called as the Gibbs equilibrium. Very easy. Understand that they can change the language in the MCQ especially. Then what they can write? They can write over here, instead of diffusible and non-diffusible, they can write permeant ion. So non-permeant ion have the effect on the distribution of permeant ion, and that is known as Gibbs. So understand, either it is going to be D or P, right? So if you extend it over here, I'll just give you an example, that is going to be P, right? So either they can write permeable ions or diffusible ions. Permeant, permeable ion, one and the same thing. Okay, so this is known as Gibbs equilibrium, and this is also called as Donan's effect. Donan's effect, right? So please remember that either they ask the question on the Donan's effect or they ask the question on the Donan's equilibrium, Gibbs equilibrium, one and the same thing. Depending on for how much marks they have asked you, you have to write all the things over here with some explanation also, right? So this is the permeant and non-permeant ion. Depending on this, what is going to happen? I can write that there is something known as Nernst equation also. What is the Nernst equation? It is going to say to us that because of these changes, I want to know that how much is the potential difference between inside and outside of these cells, right, of that particular ion. Then I'm going to put the electrode, one electrode outside, one electrode inside, and I'm going to measure that. Before moving to the different equations, just revise the chart that we have already made. 2 by 2 ka chart we have made already, that I have to write ICF, ECF, cations and anions. Cations and anions. So how many of, or which of the ions they are going to be more inside and outside? Can you help me out in the comments? Yes guys, tell me which of those. We have discussed that already, that inside I told you that the cell is a bag of potassium, but it's a monovalent ion, and that's why if they ask divalent, it is going to be magnesium, isn't it? So that means all the other ions such as sodium, calcium, they are going to be more outside. They cannot be more inside. Okay, I told you outside we require sea-like water, that means salty water. Why? Because we evolved in such an environment. That's why our body requires such salty environment surrounding the cell, and that's why in the ECF, that means either in the plasma or in the interstitial fluid, we should have more salt, that is sodium and chloride. Since the chloride is an ion, I'm writing it over here. Not only that, if I talk about the anions inside the cell, remember they start with the P and P, that is phosphates are going to be the main ones, but with that we do have some cell proteins which are going to be more inside the cell, right? The remaining ones such as bicarb, they are going to be more outside. There is no much of the difference of the bicarb, but yes, if they ask where it is more, it is going to be more in the outer environment. Okay. Why I have told you that? Because understand, wherever it is more, it is going to try to move along its concentration gradient. But there are some non-diffusible ions, they won't allow that to move along with the concentration gradient. For example, if I talk about the calcium, calcium is more outside. So what it will try to do? It will try to come inside the cell, isn't it? but there are going to be chlorides and bicarbonate. They won't allow it to go completely and have the balance in the inside as well as in the inside and outside of the cell, right? So this is the major thing that you have to know about, right? And can you tell me, if I ask you on the basis of the information I gave you, yes, answer in the comment box. So what should be the answer of this question? Sodium ion concentration is going to be more outside or more inside, that you have to tell. Compare with the intracellular fluid, the extracellular fluid has, yes guys, answer, higher, lower? Rahul, give me the answer. We just now discussed that the sodium is going to be more outside, the chloride is going to be more outside, because we require salty environment outside the cell, isn't it? And the ones which are going to start with the PPP, that is potassium, phosphate, proteins, they all are more inside the cell, right? So it is going to be extracellular fluid they have asked. So higher, lower, higher, lower. So it is going to be high outside, it is going to be low outside, it is higher, and this is also going to be low as the potassium. So that's why the answer over here is going to be option D, right? Easy question. If you know how to solve the question, if you know your concept well, nobody can stop, isn't it? So there is one very nice message that I want to give you, that you cannot go back and change the beginning, but yes, you can start where you are and change the ending. So that's why whatever happened till now in your profs and first term and all, so don't worry about it. So whatever you have, whatever time you have left till the prof, you can make worth of it via studying as much as possible, isn't it? So most abundant intracellular divalent cation, we have also discussed this. They haven't asked about the most common intracellular cation, but what they asked, divalent. So which is that going to be? Yes, please give me the answer. Is it going to be potassium? Is it going to be sodium? It is going to be magnesium, or is it going to be calcium? Which of this is going to be the answer? The answer of this question is going to be, obviously, if they would have asked just intracellular cation, then the answer would have been potassium, but they asked divalent. So that's why my answer is going to be magnesium, right? Guys, give me the answer so that we can move ahead easily and quickly, isn't it? Now, coming to the Nernst potential. How to know the Nernst potential? Now, I want to measure the potential. If I have to measure the potential, there is no direct way, right? So I have to measure the potential difference basically. So what I'm going to do, I'm going to take a cell, I'm going to put a surface electrode, and then you can see over here in the diagram, there are two electrodes. One is the surface electrode, which is there outside, on just outside of the membrane, and there is one more electrode which is going inside. That means, see over here, that this is one of the micropipette electrode which is going to be attached till here. That means what it is doing, just inside the cell membrane and just outside of the cell membrane, we are going to measure two potentials, and whatever the difference is going to be there, that is going to get represented in the voltmeter that is attached to these two electrodes. And because of that, what is going to happen, whatever changes are going to be there, they are going to be shown in the voltmeter, and that's how we are going to measure the potential difference. But there is another way, because in the exam they're not going to give us the cells, and they're not going to give us the microelectrode, electrodes, microscope, everything. What they're going to give us, the values, and with the help of values and with the help of one of the formula which is given by the scientist, that is Nernst, we can measure the potential difference between these two. Now understand, in this scenario, the scientist, he's assuming that the cell is completely permeable and we don't have any other negative ion. Okay, suppose rather than cell, I have taken the different, let's say, two tanks, right? And in between I do have a pore. So if I measure the difference of this potential across that pore, then that would be the Nernst potential. Okay, for example, let's say there is a X ion which is completely permeable. It can be positive, it can be negative, right? So let's say it is completely diffusible. That means its permeability is 1. How to calculate the permeability, I'll tell you that also. So if it is completely diffusible, that means it is having fully permeability with it. So it is fully permeable, right? So that means if there are let's say 100 molecules over here, again 10 molecules over here, so it is going to be equalizing. Why? Because we don't have any other molecules with it, right? And that means whatever difference is going to be there, that is called as the nurse potential. Okay, how to calculate that? For that I need two values. What are the two values? The concentration outside of the cell, which I'm going to write it as CO, that is concentration outside, and I require concentration whatever is present inside the cell. Okay, and the nurse have given the equation. According to that we can easily calculate it, right? So let's write the definition first. If the cell membrane is freely permeable to any ion, now there is no particular boundary that this should be semi-permeable or there should be another ions inside which is holding them. No, we haven't put any such criteria to this nurse potential right now so as to understand. So if the cell membrane is freely permeable to any ion, it will move along its concentration gradient. Move along its concentration gradient, and if we measure the magnitude of potential, we measure the magnitude of potential difference, magnitude of potential difference of that ion movement, then it is going to be what thing? It is going to be the nursed potential. It is called as the nursed potential. Okay, so it is as simple as that. Allow the ion to move and check what is the difference. So, and we have to take the magnitude. The only condition over here is you should allow it to move freely. There is no other ions inside. There is no any outside or inside force which is hampering its permeability, right? So this is called as nursed potential. Now understand, the nursed potential is for a single ion. We haven't taken any other ion and any other conditions over here. It should be for the single and one and only ion that is going to be there. So this nurse potential is also called as the equilibrium potential. And the formula that has given by the nurse is, let's write the formula over here. The nurse was a scientist who gave the formula. He said that RT by ZF, natural log of concentration outside upon concentration inside. Concentration outside upon concentration inside. Now, what are these different values? R means it is the gas constant that we have to use because we are talking about the gas. T means temperature, which we are going to keep it as constant. Usually we keep the room temperature, that is 24 degrees Celsius. And then the Z is the valency and F is the Faraday's constant. F is the Faraday's constant. Isn't it? Now understand, if I keep all these RTZF same, then what is going to happen? See over here that this over here is constant, then Faraday's is also constant, that these two values are not going to change. Then comes the temperature, which we are also going to keep it as 24 degrees Celsius, which is the normal room temperature, and just on the basis of valency it is going to change. For that matter, you just have to remember that the value overall, if I keep the valency as 1 plus 1 specifically, then the formula will be If the valency is 1, either it can be negative also, positive also. So if I keep it positive, it is going to be positive. If I keep it negative, it is going to be negative. So I'm writing both the signs over here. So this value comes out to be somewhere near around 61 millivolt. So I'm going to keep that 61 and natural log. Since the natural log cannot be easily calculated, so I'm going to change that natural log into log 10. Right, and then I'm going to write the concentration outside upon concentration inside. If I put the values that we have discussed about the potassium, that the potassium, I'll show you that diagram again, that suppose the potassium is 140 milliequivalent inside and 14 milliequivalent outside, then what will be the scenario over here? So same, let's say example we are going to take over here. Let's say this is the cell. Inside, let's say it is 140, outside it is 14. Whatever values they have to give, they will give you, you have to put that values. Okay, so if I incorporate that value, that will become, since the potassium I'm taking, so it is going to be +1, and that's why I'm going to write it as +1 in the this thing. I'm going to write it in the sign. So it is going to be plus 61 log 10. Concentration outside is 14 and concentration inside is 140. Now it's a little tricky, but this was positive. If I write negative, this denominator and numerator, they are going to change. What I mean by that, if I just apply negative sign in front of that, it is going to be negative 61 log of 140 upon 14, that is going to be 10, and we know the log 10 is going to be equal to 1. So log 10, we all know that how many zeros are there. We are going to just apply that number. Log 100 is going to be log 100 is going to be 2, log 100 is going to be 3, 1000 is going to be 3. So whatever zeros are there, we are going to apply that over here. So it is going to be minus 61 into 1, that is going to be minus 61 millivolt. In this case, this is going to be minus 61. If I'm confused in the sign, which sign to apply, just calculate it, whatever value it is coming, unless and until it's a calcium or magnesium, because then you have to divide it with the 2, right? Here the denominator is 1, valency is 1, that's why we don't have to divide it anyhow, right? But if they give you about the potassium, sodium and all the monovalent ions, then you have to just divide it and find the value. Then remember, if there is a cell and there are different ions which are present, so suppose there is a cell, this is the cell, okay? If positively charged ion is there, if it is leaving the cell, what is going to happen? Definitely positively charged ion leaving the cell will be negative. Why? Because the charges are also going to go outside with that ion, and that's why inside there will be negativity which is going to be present. The opposite thing is going to happen if I allow the positively charged ion inside the cell. So if I am talking about sodium, what is going to happen? Sodium is a positively charged ion. If I open the sodium channels, what is going to happen? Sodium is more outside, want to come inside the cell. It will bring its positive charge with it inside the cell, and it will make the cell positive also. So the cell will become positive. That means it is going to cause the depolarization, right? If I talk about chloride on the other hand, what is going to happen? Where the chloride is more, the chloride is more outside the cell. It will try to come inside the cell, but remember, this is negatively charged ion. So what is going to happen? It will bring its negativity inside the cell and will make the cell negative. And if I talk about, let's say, calcium, what is going to happen? There is another example. If I talk about calcium, it will act as a sodium again. Calcium is also more outside the cell, and if I allow it or I open the channel, it will come inside the cell, will make the cell positive. That means there are two things or two ions, major ions, which are going to make the cell positive. One is the calcium, the another is the sodium. There are two major ions which are making the cell negative, that is potassium ions via leaving the cell and chloride ion via coming inside the cell. Okay, so there are two negative major ions and two positive major ions, isn't it? Why I'm saying so? Because whenever we are going to learn about the EPSP, IPSPs, these are going to be very, very important phenomena which we have to again go over there and learn. So let's we have talked about this Nernst equation now. So let's discuss about the equilibrium potential. What do you mean by equilibrium potential? It's the same. Whenever the electrical and chemical potential, they will be equal and opposite, the movement of the cell will stop and the flux will stop at that point. That means its electrical and chemical gradient, it is equal and opposite, which happened in the case of potassium where the flux has stopped. So that means the forces on both the sides, they are equal. And that's why we are going to call it as equilibrium potential, where the movement will not occur, right? So if the movement is not going to occur, definitely we are going to say that the equilibrium potential has been reached. But remember, this is for single ion and we are not calculating other ions in this matter. So let's see what are the potentials. I'm going to start with the sodium, then comes the chloride, then comes the potassium and calcium. I have already told you the funda about the positivity and negativity, that is the sign which is going to come in front of it. Just remember the values which are very, very important. First of all, for the sodium, it is going to be around minus 60 millivolt. All of these potentials are going to be in the millivolt. Chloride, what about that? It is going to be minus 70 millivolt. What about the potassium's equilibrium potential? It is going to be minus 90 millivolt. What about the calcium? Remember, the calcium is in the range of 110 to 130 millivolt. Now remember, there is a wide range given in the different books. In some books it is written as 100 to 130 also. So that is also not wrong. It is also correct. But if I have to choose, I'm going to go more towards the 130. Right? Till now, any doubts, please let me know in the comments. Otherwise, we can move ahead. Okay. So the signs are coming accordingly. The sodium is going to be positive over here, right? And the calcium is going to be positive over here. Why? We just now discussed that both of them are more outside. We'll try to come inside, and both of them are positively charged ion. And that's why whenever they are going to come inside, they will bring their charge with it, right? And that's why it is going to make the cell also positive. So whomsoever is positive, they will spread the positivity surrounding you, isn't it? So this is going to be equilibrium potential for single ion. Now let's talk about the permeability. We have talked about the Gibbs ion. It is about the distribution of diffusible and non-diffusible ion. We have talked about the Nernst equation, which is also known as equilibrium potentials, right? And they do have different values for different ions. But the only thing you have to remember is it is because of the different ions permeability and their charges, the sign is going to change accordingly. It is given by the Nernst scientist, and we do have formula to calculate it. What is the formula? RT by ZF into natural log of concentration outside upon concentration inside. You just can turn the value upside down via giving the different charge also. Okay, we have to apply the rules of physics. I know we have left the physics behind, but somewhat physics is going to come everywhere, isn't it? Let's talk about the permeability. If I talk about the permeability is maximum for the potassium ions. That means they can fully permeable. They can go outside also, they can come inside also. But because their concentration is more inside, they try to go outside, right? So there is a value in which we are going to measure the permeability. It should be minimum, it can be written as 0. Maximum, it can be 1. So 0 to 1 is going to be the permeability of all the ions. In between, they are going to lie somewhere in between. Okay. So at the rest, if I talk, the permeability at rest, if I talk, then the potassium is fully permeable, and that means it is going to be coming as the p value will be coming as 1. So 0, what do you mean by 0? 0 means not permeable, And what do you mean by 1? 1 means fully permeable or completely permeable. As this study go inside your brain, whenever we are teaching you, the value is 1. But after 1 week, you do not revise or you do not get time to revise it, then it will become somewhere around 0.7, 0.5, right? That means the permeability will be decreasing, isn't it? Same happens in the iron also, that if it is fully permeable, the value is going to be 1. If it is not at all permeable, then the value is going to be 0. Why I am telling you? Because it is important to know. Because remember, there are 2 ions I told you, they are permeable at rest, and that is going to be potassium and chloride. These are the 2 ions. What is the permeability value for the potassium? That I am going to write as pK. In the subscript, I am going to write potassium ka symbol, and I am going to write P. P means permeability. The permeability of potassium is going to be 1. That means at rest it is fully permeable. What about the chloride? The P value of chloride at the time of rest, it is going to be around 0.45. That means 45% of the chloride is permeable. And where the chloride want to go? The chloride want to come inside the cell. It is negatively charged ion, will make the cell negative. Same in the case of potassium also. Potassium is positively charged ion. It wants to go outside because in the cell it is filled up, right? And that's why both of them are making the cell to go towards more negative. And please remember, if both of them are making it negative, and that's why the RMP, the resting membrane potential, is almost of all the cell except 1 or 2, it is going to be negative, isn't it? So that's why we say that normal polarity is negative. Why? Because at the time of rest, these 2 ions are permeable, and if they are permeable, they both are going to make the cell negative, and if they both are making the cell negative, definitely it is going to be the negative polarity which is going to take place in that condition, isn't it? Let's move on to the effect of different ions on the RMP. If you understood till here, please let me know. That potassium and sodium, calcium, magnesium, all these ion changes we are going to see. Yes guys, are you able to understand why this is happening? Why the cell polarity is negative? Because none of the book will explain you so nicely. Why? Because the books have limited amount of space, so they are going to just collaborate everything in between and they are going to write, right? They will write it as a review, isn't it? So if you understand that, everything will be very, very easy. What is depolarization? What is hyperpolarization? When the influx of some ions, I'm going to say, whether it will cause depolarization or hyperpolarization, everything will be easier if you understand what is the normal polarity, isn't it? Just give me a thumbs up, or whomsoever is watching, just let me know if you understand everything till now. Right. So let's move on to the effects of different ion. Many ions are there. We're going to see the important one which are asked in the exams, isn't it? First of all, we are going to talk about the potassium. There are 2 conditions which are possible in the case of potassium. What are those? These 2 conditions. First is hypokalemia. Now understand, wherever we are going to use the word emia, it literally means blood. Wherever the word emia is going to come, uremia, the kalemia, the natremia, kalemia, calcemia, emia means blood. Whatever changes are happening inside the blood, they are going to attach the word emia in between. Anemia means absence of the blood. Actually, it is not the absence, but the reduction in the blood cell. Polycythemia means increase in the number of cells. Poly means many cells are there, right? So that's how the emia comes. And over here we know the 2 terminologies, that is hypo and hyper. Hypo means less, hyper means more, right? And there is one thing which is coming in between, that is potassium. Potassium, symbolically we write it as K, right? And that's why hypokalemia means there is a reduction in the potassium value in the blood. Now they haven't said it about the cell, they're talking about the blood. Blood is usually present outside the cell. We have discussed what is the compartments or what is the compartmentalization which is going to happen in the body. The cell is ICF, that is intracellular fluid. Then there will be interstitial fluid, and then there will be blood vessel. If I say inside the blood vessel the potassium is low and the cell is a bag of potassium, what is going to happen? More and more potassium will want to go outside. Why? Because now the gradient has been increased. The potassium, let's say beforehand it was 14, now it became, let's say, 2 or 3. What is going to happen? The difference that was there before, now it has been increased even more. So what is going to happen? If the gradient is increased, that means the value, the difference is more. The delta value of, let's say, C, delta C, that means concentration gradient is more rapidly and more forcefully the changes are going to occur, or the movement of the ion is going to occur. So more potassium will go outside. That means what is going to happen inside the cell? If more positively charged ion go outside, that will make the cell negative. So that means if there is a hypokalemia, amia means inside the blood, then what is going to happen? There will be increase in the gradient, which will make the potassium, so more potassium will move out, and because of that the cell will be negatively charged, and that is known as hyperpolarization. Hyperpolarization. The opposite is going to happen in the hyperkalemia, but medicine is not that easy. There are going to be twists and turns everywhere, and that's why not everybody can afford to read that many things, right? So that's why we are going to discuss that. Hyperkalemia, you have to first of all decide whether it is mild to moderate or severe hyperkalemia. Okay, so we are going to divide that into two types. First is the mild to moderate, and then there is going to be severe type of anemia. In the mild to moderate, what is going to happen? The same thing that you have thought till now. Hyperkalemia, that means I'm going to say that there is a hyperkalemia means, suppose this is the cell. Outside there is going to be blood vessel. The potassium has increased over here. That means there is a less gradient. Obviously inside the cell the potassium is going to be much higher because it's a bag of potassium. So the gradient is going to be reduced over here. It's not that the opposite movement will start. Understand that. This is the delta that I have written over here. It's not A. So delta C is going to decrease. That means less potassium will move outside. In the mild to moderate, that means less potassium will move outside, and that means more of the potassium will start accumulating inside the cell. What is going to happen? There are many potassiums ions which are accumulated inside the cell, will make the cell positively charged. That means it is going to be depolarization that is going to take place over here, isn't it? So definitely it is going to increase the excitability of the cell, isn't it? So if it is increased excitability, scared of FMG due to the day before result, what we can do, we will do, right? What is in our hand? To study, isn't it, Ritesh? Don't worry about that. Read the concept. If your concepts are strong, nobody can stop you from passing the exam. I understand that this is a very bad phase, happened for many. I don't know why the paper was tough or it was very lengthy, and some are saying that our preparation are up to the point, but we haven't crossed that. The reasons can be many, but yes, definitely what we can do, we will do. Hello Gajendra. Definitely, right? So let's do what we can do right now. I know many of you are scared, but we cannot do anything. The feelings are going to come, but we are bigger than that. We have to look ahead. I know it is going to feel bad for some who cannot cross through the exam, but definitely what they have is next 4 5 whatever months are there, they can prepare again rather than cribbing on whatever the result has come, because again we cannot change the result right now. What we can change is the present, and what we can change is the future. We cannot go back in the past and change it, but we can use our present to make our future better, right? So let's start. If there is a less potassium moving outside, what is going to happen? More will be accumulated inside. Right? More is accumulated inside, more positively charged ion accumulating inside. What is going to happen? That will lead to depolarization. And please remember, is very, very, very important. Why I'm saying so? Because when you go to the internship and you're going to see the patients, suppose you pass your postgraduate NEET PG also, then what is going to happen? Definitely you're going to see the patient and you will be more worried about the potassium levels. Why? Because understand, if there is even slight hyperkalemia, what is going to happen? If sodium is more or less, there is a range which is wider than the potassium, we don't worry about that, but we worry about the potassium levels a lot. Why? Because even the moderate hyperkalemia, it can lead to such a drastic changes that it will lead the cell to depolarize. What is the risk? The risk is that we do have heart in which this is going to affect, right? And it will make the heart to go in the arrhythmic condition. So arrhythmia is going to take place. And that's why this is very, very important to know that whatever potassium values are there, we have to maintain those values. Usually you're going to be worried whenever the patient is going to get admitted into the ICU, you're going to ask for the electrolyte changes, and the first thing you are going to see is the potassium value, because you do not want the patient to go in the arrhythmic condition, right? And that's why we have to make sure that the potassium values are appropriate or adequate in those patients. Okay. Coming to the severe one, what is going to happen in the severe? There is something known as persistent depolarization which is going to take place. It is not easy. Listen, the medicine is not easy. The slightest change will become more, give the very different result that we have expected, isn't it? And that's why we have to revise many times, because different scenarios are going to come with the different types of patients are going to come, right? It's not like learn one formula and go in the exams, which is happening in the engineering phase, which is not applicable in the medicine, and that's why it is more difficult to grab everything up. Okay, but we are going to try. So in the severe condition, what is going to happen? That in the severe hyperkalemia, there is something known as, I told you, that persistent depolarization is going to take place. Now understand, I'll give you a very easy example. You started to read. What happens first 20-25 minutes? Your concentration is very nice, right? So everything seems to be very digestible, very understandable, that we can recall it. But after, let's say, 45 minutes, 1 hour or 2 hours, what is going to happen? Our concentration level goes down, and whatever we are reading, it just do not get into our head. So same thing happen with the cell also. So same thing, that means the depolarization is so continuous that the cell will adapt to that situation, and cell thinks that this is my normal level. So it stop giving any stop giving any signals to the cell, or stop making any excitability. So overall, what is going to happen? Just make a note of it over here, that the excitability is going to decrease rather than increasing. If you push anything too hard for too long time, what is going to happen? It tend to give you the different result as you expected, right? So take smaller break. Take smaller breaks, and then, yes, Umesh, just don't worry about it. We'll cover everything, right? For now, just remember whatever I'm telling you over here, right? In some books, the values are going to get different. Why? Because none of the physiology books have given this values, okay, but definitely if it is within the range of 2 to 3 milliequivalent per liter, we usually say this is the mild one. If it doubles up, this is known as moderate, and if it goes more than that, we call it as the severe one, okay. But definitely I would like to confirm that in the what is given in the latest edition of Harrison, and I'll let you know, okay. I was talking about persistent depolarization, that continuously, let's say from few days, the potassium levels are higher outside. What is going to happen? More potassium will remain inside the cell, and the cell will adapt to that situation and stop making the action potential. If it is for prolonged duration and for severe hyperkalemia, for prolonged duration, it will stop making action potential. Severe hyperkalemia, for prolonged time, stop making action potential even after reaching the firing level. It reaches to the firing level, but it won't make the action potential. I told you in the cases of when we discussed this last lecture, we have discussed about the accommodation and adaptation in the nerve properties, right? Properties of nerve. In that I told you that slow rising current also do something similar with the sodium ions, but it's the somewhat little bit different phenomena, but somewhat similar also. They also reach up to the sodium, even if they reach up to, the value reaches up to, or the potential reaches up to firing level, it won't produce the action potential. Over here, first of all, it will produce the action potential, but then initially after making the action potential, after some time it will stop making the action potential if it is prolonged, okay. So this is known as the persistent depolarization, which will stop making the action potential because the cells are going to get adapted to the new set point, okay. So this is going to be different scenario over here. Coming to the effect of ions on the RMP, what this meme is telling you, I don't have always influence membrane potential. No, I don't always do that, but definitely whenever it comes on to the action, definitely it is going to make the changes, right? So that means what the message it want to give us, that sodium has no effect whatsoever on the RMP. Why? You have to answer me in the comment box. Give me the answer in the comments box. I'm going to wait for the sodium, why it doesn't affect the RMP. Coming to the calcium. Now, I told you the calcium is going to act as a guard. Okay, so if more guards are there, what is going to happen? The sodium won't come, or sodium won't be able to come inside, or there is something known as non-selective channels which are open at the rest also. They won't be able to allow the positively charged ions inside. And because of that, what is going to happen? The reverse scenario is seen. That means if the calcium is more, what you are going to call it as? It will be called as hypercalcemia. If the calcium levels are low, it will be called as hypocalcemia. So they will block the non-selective cation channels, or they can block the sodium channels also. Sodium, we usually talk in terms of the action potential. Why? Because they are not at all permeable at the time of rest, right? In the guidance, it is written that some of the leaky channels which are present, which can allow the sodium as well as calcium to come in. But remember that the calcium are bigger in the size, and that's why the sodium try to leak out into the cell. And that's why we require sodium potassium ATPase. Otherwise, there is no need of sodium potassium ATPase, isn't it? But remember, in the resting condition also, some sodium try to come inside. Okay. With that, we'll move on forward, that the hypercalcemia, calcium is acting as guards, so it won't allow more of the cations to come inside. That means what is going to happen? If the guard is not allowing the positively charged ion to come inside, it is going to cause the RMP to go in the negativity. So it will lead to hyperpolarization, isn't it? If less guards are available, more cations can come inside, which can come through the leaky channels at the time of rest, and that's why hypocalcemia will lead to depolarization because less guards are available there. Right, less guards are available, so more cations can come inside even during the rest. What about the sodium? The p-value of sodium, that is the permeability of sodium, is almost 0. It is almost 0. In the guidance it is written as 0.04, and that 0.04 comes through the non-selective cation channels. Okay, so it is almost 0. So if they specifically ask about sodium, tell upfront that the sodium has no role in RMP. And that's why it is saying that it does not always influence on the RMP, and definitely when the time comes for the action, it is going to show the action. That means it is going to have the effect. Okay, why? Because the p-value is almost 0, and that's why no matter what is happening in the blood, either the sodium increases, decreases, there is no permeability. Right, whatever permeability is there, that is through the leaky channels, and leaky channels have very, very low potential, which is allowing the cells to come inside. So that's why it won't affect the cell depolarization or repolarization much. Right, Ritesh, you are right that this is going to excitability is going to be decreased if there is a hypercalcemia, isn't it? So excitability is going to be decreased. Hyperpolarization means decrease excitability. Depolarization means it is going to go near to the threshold. That's why that increased excitability is going to be there. Talking about one more thing that is known as the two names, or rather three names you have to remember. What is that? That is GHK. What is GHK? Goldman, Hodgkin, Katz's equation. Now what is that? We have learned two names already, that is the Gibbs-Donan and Nernst equation. Gibbs-Donan was telling us the effect of non-diffusible ion on the diffusible ion, distribution of diffusible ion, and the Nernst was telling us the equilibrium potential. Okay, the GHK is going to tell us the whole RMP. What is the difference between these two? RMP, you have to summate all the ions together. Remember, I specifically wrote as the Nernst equation or equilibrium potential is for single ion. But at the cellular level, that is not the only one ion which is going to move at a time. There are going to be many ions which are present inside also, outside also, which are going to affect the RMP. So that's why the resting says you have to see how many ions are there outside, what is its charges, and you have to add them up. So in total, what I can do is, I can calculate the RMP value, or I can calculate the Nernst equation for everything, or equilibrium potential of all the ions at the time of rest. Or what I can do is, I can use a simplified formula, that is RMP is equal to the summation of what thing? Let's say permeability of equilibrium potential of X ion into permeability, or other way around, you can write equilibrium potential of X ion into its permeability of X ion plus equilibrium potential of Y ion into its permeability, so on and so forth. How many ions you are having, you can add them up. Okay, if I wrote over here that let's say X is the potassium, so definitely equilibrium potential of potassium is going to be there, and into 1, that is the fully permeable ion is there. So that's why I'm going to write permeability of potassium over here. If I have to write about the sodium, what can I write? EP of the sodium, no matter what it is, right? The permeability is 0, so anything multiplied by 0 is going to be 0, right? So it is not going to have any effect. Again, the hypothesis which was given, that stands true, right? So this is going to happen over here. And that's why even if you allow all the ions to pass the membrane, what is going to happen? If I say that all ions are permeable at rest, RMP is going to be 0. if I do not allow anything, that means if I make the p values of all the ions 0, that means I'm not even allowing the potassium to move inside. Completely impermeable membrane is there of the cell. Then what is going to happen to the RMP? RMP is also again going to be 0. Why? Because the p value of all the things are going to be 0, 0, 0, right? So please remember, whether you allow all the ions, what is going to happen if you allow all the ions? They will come to one point where all the ions are equal on both the sides, so there is no movement. If there is no movement, there is no potential difference. If there is no potential difference, everything is going to be come back to 0 back again, right? So this is how it is going to take place. So you can add whatever levels you want, right? Just remember, you can either calculate the equilibrium potential of all the things, or you can just write this formula that is given by the Goldman, Hodgkin, Katz. They were the 3 different scientists, right? They came together and they came onto this formula that equilibrium potential multiplied by its permeability. If you summate for all the ions, it is going to give you the value of RMP, and that's how we are going to calculate the RMP for different structures, isn't it? Let's move on to the question. Can you tell me the answers? Urvesh, Ritesh, Gajendra, Rahul, tell me what is the answer over here of this question. Read the question. I have given the hint also already. I'll tell you the hint again. The distribution of diffusible ions between 2 compartments separated by semi-permeable membrane. So semi-permeable membrane is there, so it is kind of a cell-like condition. In the presence of non-diffusible ions will be called as, yes please, what it is going to be called as? Tell me once again. Hanji, what it will be called as? I'm waiting for your answers. Yes, Ritesh, you are absolutely wrong. Sorry to say that. I have given you the hint also. D. Try again, Ritesh. Try again, bache. What I told you. Distribution of diffusible, non-diffusible. How can it be nursed? It cannot be nursed. What it is? D. That is Donan's equilibrium. Okay. Do as many mistakes as you want. Yugal, you are right. You're absolutely right, bache. So please remember, if they give you permeant ion, non-permeant ion, diffusible ion, non-diffusible ion, what you have to write is Donan's effect. Nernst equation kab bologe? Whenever they are going to ask you about the single ion ka equilibrium potential, right? So please remember, Nernst is, there is E is coming, right? There is no E in the Gibbs Donan. So you can remember that ways also. Nernst is for equilibrium potential. Equilibrium potential. So remember, don't forget, do as many mistakes as you want over here. Most welcome to do the mistakes. Why? Because if you do the mistake over here, there are least probability that you are going to repeat that again. Okay, so that's why you have to answer. Yes, Ritesh, absolutely correct now that the Nernst is for equilibrium potential. E is there, right? And there is a Donan. So please remember, if they are talking about distribution, then definitely it is going to be the anything distribution. The distribution word is going to be there. Diffusible or non-diffusible you can remember, or permeable and non-permeable ion you can remember. Henderson-Hasselbalch equation, that is for HH is coming. So please remember, it is for pH, right? So Henderson-Hasselbalch equation is there. HH is coming. So hydrogen ion concentration, usually we talk about pH. So HH is for pH. Remember that. Okay. And what about Hodgkin-Huxley-Katz equation? There is no such thing, right? First thing, Hodgkin they have taken from somewhere else. Huxley was given the action potential, how the action potential moves and what are the ions that are going to move during the action potential. So it should be Goldman-Hodgkin cat equation and not Huxley-Hodgkin, right? So first of all, this is wrong. The Goldman-Hodgkin, on the other hand, GHK equation is for RMP, resting membrane potential. Okay, so this is the thing. Yes, your next answer should be 100% correct, 200% correct. Now tell me the RMPs of different values of RMP. Let's talk about it. Neurons. It is very similar to the chloride ka equilibrium potential. What was the chloride ka equilibrium potential? Tell me, EP of chloride was how much? Remember, I told you that in most of the cells, the permeability at the rest is going to be for chloride as well as potassium. So most of the cells, you can see over here, I have given the negative signs, whatever cells I have told you over here already, right? Ritesh, absolutely right. It was minus 70. So same over here, minus 70 is going to be, that is millivolt. It is going to be the resting membrane potential of the neuron. Now understand how to remember. The skeletal muscle and cardiac muscle, both of them have similar ones. The Genong itself writing two places, two different values. In the CVS, it is written that cardiac muscle having minus 90, and in the general, at one point in the 24th edition, it has written as minus 85. So minus 85 is also correct, minus 90 is also correct. Okay, but don't worry, they are going to give you either of the value. Not both of the values will be there, right? Even if they are there, go for minus 90 MV, because everywhere in the guidance it is mentioned as minus 90. I'll check the latest edition of Genong also today, right? So skeletal and cardiac muscle, both, please remember, it is going to be minus 90, which is the highest, right? So how you can remember? You can remember that it requires more potential to produce force. The cardiac muscles are going to produce the force in the systole throughout your life. So that's why it requires more potential. What about the skeletal muscle? Skeletal muscle contractions are required to put or to act against the gravity, even for the throughout whenever you are maintaining your posture. Whenever you are not lying down supine, that means your skeletal muscles are active, at least your postural muscle. Now I am sitting upright, that means my back muscle, my other postural or my anti-gravity muscles are activated so that I can maintain my posture, right? And that's why it also contains maximum of the potential, RMP, resting membrane potential. What about smooth muscle? Everything it is nearby the minus 50. Even they say that the cardiac muscle ka nodal tissue was there, that is modified cardiac muscle. That is, if you have to choose between one value, then you can choose the minus 50 MV. Okay, but remember, it has non-stable value, which is minus 40 to minus 60 MV, which we have discussed in the CVS lectures also, right? What we discussed, there are two pacemakers which are having non-stable RMP, which is going to be the cardiac muscle pacemakers and the GI pacemakers, that is interstitial cells of Cajal, which are going to maintain the fluctuating RMP, that is from the minus 40 to minus 60, or you can say minus 60 to minus 40, because minus 60 is again towards the negative. So please make a note of it. SA node ka minus 40 to minus 60, and the cochlear cells and thyroid cell, they are usually minus 40 to minus 50. Okay. What about rods and cones? Yes, Ritesh, you are absolutely right. What about rods and cones? Minus 30 to minus 40. Only once this was asked in the NEET exam, that too very old question, that is 2018 NEET. This was asked. Otherwise, it is never asked or never repeated, right? But you have to remember that, because it is, everything is more near towards the minus 50. If you do not know, because most of the cells, they match to the smooth muscle. There is a list given in the Boron, and most of these are nearby minus 50. If you do not remember, either it is going to be asked neurons, skeletal muscle, smooth muscle. If they are not that, just remember about the RBCs. It is going to have least RMP, because no action is required in the RMP, this RBC. Why? Because it just have to transfer the gases, right? And that's why it is going to be least. So the question was asked once in the DNB exam, and the option given over here was minus 10. Okay, so please remember, the least value of the RMP is of RBC. Okay, so they are resting all the time. Okay, So please remember the RBC are the all cells except the neurons, skeletal muscle, cardiac muscle and smooth muscle. You can remember it as -50 के आसपास. Okay. Let's move on to the genesis of RMP, how the RMP is generated. Now, if I have to measure, see over here in the diagram, just inside I'm going to put the micro electrode. You can see is a very needle-like electrode which is I'm going to insert so that it will reach up to the inner surface of the cell membrane, and one surface electrode I'm going to attach, which is attached over here, and both I'm going to connect it to the voltmeter so that whatever change is there, whatever difference is there in between the potential outside the cell membrane and just inside the cell membrane, I can measure that, and whatever value is going to come, that will be my RMP, isn't it? What is the major two factors which are affecting the RMP? The factors affecting, they are the equilibrium potential and permeability, isn't it? They are the major two factors. If the equilibrium potential of that particular ion is more, the RMP will be more. The permeability, if they are not permeable, they won't be affecting the RMP, such as sodium ions, right? But if they are permeable, they are definitely going to put the RMPs to change. Now understand that if I write in the order that who affects the RMP more, then the most effective or effective ion who can do the changes in the RMP is potassium, which will be followed by the chloride ion. Why? Because their permeabilities are higher in the resting state, isn't it? And then comes the sodium potassium ATPase. Please mark that it is sodium potassium ATPase and not the sodium. If they ask about the sodium, please understand, na. That means there is no role of sodium in the formation of RMP. Na. That means no means no, right? So please remember, sodium alone won't be affecting the RMP, but yes, if they ask about sodium potassium ATPase, it will be affecting the RMP. How? We'll see that in the next few slides, right? So see over here, if this is the sodium potassium pump, we know sodium potassium is the active pump, right? And if someone asks it that suppose this is the sodium potassium pump, then someone asks it what did it cost, it is going to say ATP. Why? Because this is the sodium out, potassium in, ATPase. ATPase means definitely it requires ATP. That means it is going to be active transport which is happening over here, right? So let's learn about few points about the sodium potassium ATPase. Remember, it comes as the short question also in all the university exams. If I have to write few points, first point you have to write is this is present in all the cells. Whatever cells are there in your body, this sodium potassium pump is going to be present in all the cells. If something is present everywhere or in all the cells, we call it as universal. Anything which is present everywhere or in all the cells, we call it as universal, or we can call it as omnipresent, isn't it? Everywhere it is present, so we are going to call it as omnipresent, right? The fear is omnipresent to fail the exam, which is there, right? But don't need to get scared. We just can try. Okay, everyone feels that every time. Even we as a teacher fear of forgetting everything in between, and that's why we again and again revise, right? So omnipresent or universal means it is everywhere. It is there with the DNB people also that someday the students are going to come and blast our office, right? They must be having that fear because they are giving such a tough paper first of all, and then they are not putting up the proper results maybe, right? Now, what is the coupling ratio? Understand, if I talk about the sodium potassium ATPase, what it does is, suppose this is the cell boundary or cell wall, and if I have the sodium potassium ATPase over here, what it is going to do, it is going to throw out the sodium, Why? Because I told you there are leaky cationic channels which are present, so it is going to throw out the sodium. Sodium is already more outside, and that's why if it is throwing the sodium out, definitely it requires the energy, and that's why I have given the name as Nokia. Nokia means sodium out, potassium in, ATPase, isn't it? So please remember, it throws the sodium out, it takes the potassium in, and it also uses the ATP. So that means it is the active pump, right? And how many sodium it throws out? Carefully see over here that there are 2 letters in the sodium. That is a symbol of the sodium. Just add 1 into it. How many it becomes? It becomes 3. So it throws 3 sodium out. What about the potassium? The potassium is going to come inside, right? So it is going to throw the potassium in, because we have written it already over here. In the symbol, how many letters are there? Only 1 letter. Add 1 into it. It becomes 2. So please remember, 2 potassium inside. So 3 sodium out, 2 potassium inside, and that with the use of ATP, and that's why we are going to call it as ATPase. Okay. And this is the coupling ratio. What do you mean by coupling ratio? That how many sodium it is throwing out and how many potassium it is taking in. So what will be the coupling ratio? Coupling ratio will be 3:2. Coupling ratio is going to be 3:2. Easy? It cannot be any more easy than this. That please remember how many alphabets are there. Just add 1 into it, and with the help of Nokia, which was the first, very famous phone in the India, that is going to be helpful for the mnemonic itself, isn't it? So coupling ratio. Now understand that if this is the coupling ratio and it is using the energy, that means it is going against the gradient, and it is using the energy, that means it is the maximum. It is using the maximum energy at the time of rest. For what thing? Just simply to put more sodium out and keep more potassium in. Why? Because I already told you that if anything goes wrong, or if there is no ATP, we are going to see there are going to be bursting of the cell which is going to take place. But remember, if I remove the gradient, there will be no potential, there will be no RMP, there will be no action potential, nothing will take place, everything will come down to 0. And that's why whatever gradient we have to maintain, it is maintained by this pump, and that's why we are going to use the maximum energy even at the rest. That means you're lying down on the bed, you're not doing anything, right? Still your body uses the energy to maintain the gradient of sodium and potassium. So please remember that it maintains, its only function is to maintain high sodium outside and high potassium inside. What do you mean by outside and inside? Of the cell that I'm talking, outside means I can write ECF, in the ECF, and over here I can write in the ICF, that is intracellular fluid. Okay, so high sodium, high potassium. Otherwise, the gradient will be over. No RMP, no AP, nothing will happen. The patient will die. He will go in arrest. Okay, and that's why we have to maintain the gradient. Let's move on. If I have to talk about the different points, so you can draw a diagram, a simple diagram. If I have drawn over here the simple ATPase. If I have to draw a particular ATPase, it is going to have 2 different proteins. You can draw with me any shape, you can draw whatever you want. Okay, so this is going to be beta unit, but remember there are going to be 2 units. Heterodimeric protein is going to be there. Hetero means 2 different proteins are going to be there, and there are going to be the dimers, that means 2 subunits are going to be there. There is going to be alpha subunit and there is going to be beta subunit, and there are going to be 5 different positions or 5 different binding sites are going to be there, right? It has Nokia, or the sodium potassium ATPase, it has 5 binding site. Now if I ask you that on which of this subunit it is going to have these 5 different binding site. So please remember, it is the alpha which is going to be usually what we call the males. They are very much fascinated with the alpha thing, right? So we are going to draw a little bit bigger the alpha molecule, right? So alpha means the masculine, right? So over here also the pump has the alpha and beta subunit. All of them, the 5 sites are going to be there on the alpha. So you can write 2 outside and I'm just making 3 inside. How to remember? Just remember that whenever you have fatigue or you're tired, what do? You sleep, right? So take a nap for that while. So that is the mnemonic we are going to use over here. Okay, take a nap and restart again, right? So see over here, there are 2 subunits which are shown already, alpha and beta. And as I told you, all the 5 binding site will be there on the alpha. Then why the beta is required? Remember, the glycosylation of the beta unit is required to activate the alpha. So if the beta unit is not there, there will be no glycosylation. And if there is no glycosylation, the alpha won't act. So it requires beta to get activated. So for the efficiency, we do require the beta subunit also. So let's write O and K. Okay, these 2 are outside. O for outside. So remember, O, that means Woven binding site. Woven binding site. Or we can write over here the digoxin, digitalis, they also bind in that site, on that particular site. So you can see Woven is, this is the binding site of it. Then K for potassium. In the Nokia also the K was for potassium. And if I talk about the inside, it is the sodium binding site. Remember, I have to throw the sodium from inside to outside. So I'm going to grab the sodium from inside and this alpha subunit will flip. As soon as it is going to flip, it will release the sodium outside. Same way, it is going to bind to the potassium from outside and it is going to hold it. As soon as it is going to flip inside the cell, it will release the potassium, and that's how it is going to flip and change the position of the ion, right? Then what about the A? It is the ATPase or ATPase site or ATP binding site. ATP binding site. And to make the energy viable, I have to remove the phosphate group from the ATP, and that's why I require the phosphorylation site also for the energy release. Phosphorylation site. That means ATPase is going to act, it is going to release the phosphate from that, but again for the next cycle I require the phosphorylation of the ATP or ADP for that matter. I require these sites. So please remember, this is a very simple mnemonic. OK, NAP. Okay, so Nokia and OK, NAP, they are going to help you out. You can write these points in the exams and definitely you are going to get half or 1 mark extra. We have already discussed that even during the rest, it is ultimately important to maintain the RMP, otherwise everything will stop, right? There will be no movement of any ions, not even in the heart. So that's why we have to make this gradient to work all the time, and we have to activate this sodium potassium pump everywhere all the time, even when you are sleeping. Okay, so responsible for maximum active transport. That means this is using maximum energy, and that too at rest. So that means since it is doing the maximum active transport at rest, it is using maximum energy, and it is responsible for maximum metabolism at rest, right? So it is responsible for maximum metabolism, and I can write it as basal metabolism also, and hence it is responsible for basal metabolic rate. You must have seen many people that they say that whatever these people eat, they don't gain weight. Why? Because their basal metabolic rate is very, very high. And even some people drink the water, they get swollen up, right? So basal metabolic rate. That means if the people are eating more but they're not gaining weight, that means their basal metabolic rate is higher. At the rest also they are burning more calories. Okay, so this is dependent mainly on this sodium potassium ATPase, right? Testosterone is one of the hormone which actually indirectly, not directly but indirectly stimulate this, and that's why usually you will see that the males are going to have more basal metabolic rate as compared to the females, and that's why females tend to accumulate the fat very quickly as compared to the males. Okay, in the old people, what is going to happen? The efficiency of these sodium potassium ATPase pump will decrease. So there is going to be decreased activity of sodium potassium ATPase, right? And that's why if the sodium potassium ATPase activity is decreasing, what will happen to the BMR? The BMR will also fall, and that's why you can see in the elderly people, they do have less hunger. Why? Because the BMI is less, the requirement of energy is also very, very less, right? So you have learned very important thing today, that hi Kailash. So you have learned important thing today, that the older people, they do have lesser hunger, they do have lesser metabolic rate also. Coming to the electrogenic pump. Now, see over here, in the diagram itself, we said that 3 sodium out, 2 potassium in. Now, if I have to calculate the potential over here, I can in the simple format, I can calculate over here that inside the cell and outside. If I'll draw in on another side, suppose this is the cell, it is throwing 3 sodium and taking in 2 potassium. Both are positively charged ion, right? So both are positively charged ion, and what it is doing, 2 positive inside and 3, let's write first sodium, so 3 positively charged ion it is throwing out, right? That means 3 negatively potential, let's say if it is 1, so 3 negativities are accumulated inside the cell. Then comes 2 positive in. If I give someone 3 rupees, instead of that returning me 3 rupees, they only return me 2 rupees, right? So that means I'm in the loss of 1 rupee. Same over here, from the cell, within the cell, the 3 positive went out, but only 2 came inside. So I can write there is a loss of 1 positive in the cell, alright? Or I can say that there is a gain of 1 negative inside the cell, isn't it? So either you can write gain of 1 negative, or you can write the loss of 1 positive, one and the same thing, and that means it is actually helping in the RMP, isn't it? Why? Because it is also in the resting, it is active, right? In the resting condition it is active, and in the resting condition it is making the cell more negative, and that's why it is generating the electrical potential even at the rest, and that's why it is known as electrogenic pump, because it helps in the RMP or production of RMP. Production of the RMP. Please remember, the only value over here, in some books it is written as it contributes very less, 5 to 10% only, but remember it does contribute, and that's why when we were talking about the contribution, we have talked that the potassium is going to contribute maximal, then the chloride, and then comes the our sodium potassium ATPase. So definitely sodium potassium ATPase is going to contribute, not the sodium. Okay, so it is known as electrogenic pump because there is a gain of 1 negative ion. And remember, I'm talking about the single exchange. If I apply or I see the whole cell, there will be thousands and thousands of sodium potassium ATPase which are going to be present on the cells, and they are active all at the same time. So that's why there is going to be lot much negativity which is going to be generating, but their contribution is minimal. Why? Because it won't contribute as it is contributed by the potassium or the chloride. So we can write there is a minor role, only around 5 to 10% 5 to 10% is the contribution in the RMP. Okay, let's move on to the next thing. The clinical applied of this, that is, if there is a hypoxia or ischemia, what is going to happen? Hypoxia, what do you mean by that? There is less of the oxygen supply. What do you mean by ischemia? I told you emia means blood, ischemia means decrease or absence of blood over there, right? So either you decrease the supply of oxygen or you decrease the blood supply itself. Ultimately, if the blood supply is decreased, that means nutrients are decreased, and the oxygen, obviously, that is also going to decrease. In both the condition, what is going to happen? The production of ATP is going to reduce, because in the aerobic metabolism, we tend to produce more ATPs as compared to the anaerobic metabolism, isn't it? So that's why even if you decrease the oxygen or in the blood supply, if it is decreased, what is going to happen? Both of them will lead to decrease in the ATP supply. If the ATPs are decreased, will the sodium potassium ATPase will be able to work? No, it won't be able to work properly. So what will happen? The activity of Nokia pump, that is sodium potassium ATPase, is going to decrease. What will happen? Will the sodium able to go out? No, the sodium will start to accumulate inside the cell. So sodium won't be able to go out. So sodium accumulation will start inside the cell. If the sodium accumulation will start inside the cell, what is going to happen? I told you sodium is a crush of water. Wherever sodium goes, water follows. So what is going to happen? After looking at the sodium which is inside the cell, it attracts the water, right? So water also start to increase water accumulation inside the cell. Write it completely. Accumulation inside the cell, right? So if the water accumulation also start inside the cell, what is going to happen? Definitely the cell has boundaries and it has limits. After some time it is going to burst. But in the meantime, if we give the start the supply of oxygen, what is going to happen? The changes will be reversible. So this is going to cause, this water accumulation will cause the cell injury. But in the accurate amount of time, or initially if we start giving the oxygen back again, or whatever problem was there because of which there is hypoxia or ischemia was occurring, if we treat the cause, definitely the oxygen supply will be provided back, or the ischemia will be removed, so the blood supply will be provided, and all the things will start getting normalized back again. And that's why it's important to treat the patients very, very quickly. And this water accumulation will start bulging out the cell from one side unless and until it bursts, which are known as hydropic changes. We don't have any issue with the sodium accumulating inside. It is the problem with the water that comes behind it, and that's why it will lead to hydropic changes. But remember, this is reversible. It is not the irreversible injury. It is reversible, that in the initial movement, if you start giving the oxygen back again or blood supply back again, it will be reversible, right? If they ask in the pathology, whenever you are going to go in the second year, you are going to learn about the most common cell injury. Please remember, it is the hypoxia. There are various types of hypoxias are there, but most common type of cell injury is going to be hypoxia, and because of which these hydropic changes will start and cell can go into the morbid condition. Okay, let's move on to the next thing. What are the things, or what are the substances, what are the hormones which can stimulate the activity of this sodium potassium ATPase, or stimulate the numbers? That means either in the terms of stimulator, we can say that it can increase the numbers of the cell, numbers of the sodium potassium ATPase on the cell, or it can increase whatever cells are there, or whatever numbers of sodium ATPase are there, it will stay like that. The numbers won't increase, but the activity may increase, or both can happen. So either the number will increase, or the activity of whatever pumps are there already, their activity is going to increase. It will also cause the stimulation, or both the things can happen simultaneously. How to remember? There is a short mnemonic, very sweet mnemonic I have for you, that when you want to stimulate someone, right? When someone is going on the war, what you do? You apply some tika like thing, right? So you must have known tika. So right over here, tika. Okay. So what do you mean by tika over here? So T means thyroid hormone. Then comes the insulin, catecholamines, and aldosterone. These are the things which are going to act as a stimulator. What they are going to do? The thyroid is going to increase the number of sodium potassium ATPase. I'm just writing Nokia over here, right? Insulin, this one and this one, that is insulin and catecholamines, they are going to increase the activity of the sodium potassium ATPase. And the aldosterone, what it is going to do? The aldosterone is going to act as both. It is going to increase the number, I'm just writing it this as number, as well as increase in the activity of already existing sodium potassium ATPase. So definitely the sodium potassium ATPase is going to be maximally stimulated by the aldosterone. Why? Because it is increasing the number also, and the activity of existing sodium potassium ATPase also. So both are going to get activated over there. Let's move on to the next thing, that is sodium potassium ATPase. What are the inhibitors of that? Inhibitors are, you have to remember, it is DDD, right? What is DDD? First is digitalis, diuretics, dopamine, but dopamine not in the brain or anywhere else, only in the kidneys. Please remember, dopamine in the kidneys, and ANP. What is ANP? From the atria, that is right atrium and left atrium of the heart, the natriuretic peptide is released. So this is known as atrial natriuretic peptide. Atrial natriuretic peptide, which is going to get released, right? Let's see what they are going to ask you. Natriuresis, that means they are going to cause sodium excretion from the urine itself, and that's why they act as an inhibitor. If sodium is not there or more outside, so gradient will be less, right? So that's why through the leaky channels they are going to leak less towards the inside. So that's why this is going to indirectly act as a inhibitor. Okay, now understand, they are going to ask you about the digitalis, which is very, very important, the mechanism of digitalis. How they are going to act? They are going to directly inhibit the cell. Let's draw that and understand. It is going to be very, very helpful to increase the contractility also. We have discussed that many times. Let's quickly revise that again. Suppose this is the sodium potassium ATPase. Specifically, I give that drug in the cases where I need to increase the contractility, and in the heart we do have sodium calcium exchanger, right, which is going to throw the sodium in and which is going to throw the calcium out, isn't it? Now understand, if I start to inhibit this cell, so the digitalis is going to act and inhibit this cell, right? Let's write digitalis. Now remember, the sodium calcium exchanger, this is the secondary active type of transporter. What I mean by that, this the sodium potassium ATPase is going to create or generate the gradient. Okay, it is going to throw out most of the sodium out. That's why the another gradient will be created. And what is that gradient? That With the help of this creation of the gradient, when the sodium potassium ATPase is going to throw out the sodium out, there will be less of the sodium which is going to be available inside the cardiomyocyte, and this gradient is created. Using this gradient, this sodium calcium exchanger, it doesn't use any different ATP. It is going to use that gradient created by the primary pump, and it is going to throw the sodium out. But remember, we are moving one positive ion inside, and we have to maintain the electrical balance also, electrical chemical balance, or we say electrochemical balance. But most of out of these two, that is electrical and chemical, the electrical ones is preferable. So that's why when we were throwing out the sodium in, we are going to exchange that with the calcium. That means I'm going to throw out the calcium out. But if I inhibit the sodium potassium ATPase, there will be no gradient created, right? Digitalis is going to inhibit the sodium potassium ATPase. There will be loss of gradient, or sodium gradient, we can write gradient of the sodium. So the NCX will be inhibited indirectly. So the calcium won't able to move out. If it is not able to move out of the cardiac cell, what is going to happen? This calcium, I told you, it's very, very important for the contractility. So what is going to happen? The calcium start to accumulate inside the cell. And calcium is the positively charged ion, plus it is going to do what thing? Calcium won't be able to move out, right? Calcium start to accumulate inside the cell. Calcium requires for two things. In the nerve, please remember, or in the various places, it is responsible for exocytosis. And the second major thing it does in the muscle specifically, that it causes contraction. So over here, the overall force of contraction will be increased. So whenever the heart is going to go in the failure, I'm going to give the digitalis, digoxin like drugs which are going to block the sodium potassium ATPase, and depending on which the secondary active transport will be hampered, and that's why the calcium won't be able to go out. If it stays inside the cardiomyocyte, it will increase or enhance its contractility without increasing the heart rate. Heart rate, if it is going to increase, the workload is going to increase on the heart. The heart has to do more work. Remember already that heart is failing. You ask him to do more work, it is going to fail very rapidly. So that's why we cannot increase the heart rate. So that's why we have to increase the cardiac output. That means we have to increase the contractility of the heart and not the heart rate. So we can do that with the help of these drugs. So they are going to be very, very helpful to us. Okay, let's learn about the changes in the RMP. How we can know the changes in the RMP? Let's say I'm going to draw axis over here. On the y-axis, I'm going to write potentials. Let's take minus 70. All right, above which it is going to be minus 60. Let's say minus 50 over here. Right, let's say minus 80, minus 90, so on and so forth. Okay. Now, if I say that I give, let's say, plus 10 millivolt stimulus, what do you think will happen? The resting membrane potential was minus 70. If I give positive plus 10 stimulus, it is going to increase by plus 10, right? So, the potential will change, go on to the minus 60, and it is going to come back again, isn't it? If I give, let's say, plus 5 millivolt stimulus, what is going to happen? It is going to go plus 5 and it is going to come back again, isn't it? Same, if I give hyperpolarizing stimulus, let's say I give plus 20 millivolt stimulus, what is going to happen? It will go in the negative and come back. If I give, not positive, it should be minus, negative, and negative 10 millivolt, what is going to happen? It will be something like this. Now understand, if I talk about the synapses, what do you mean by synapses? We were learning about the cells till now. If I talk about the communication between two neurons now, that is known as synapse. If I measure these changes, if I try to stimulate the neuron first of all, and check the responses in the another neuron, right? And same I'm going to do with the different ions. So what I saw over here is that some cells will inhibit the other neuron and some cell will stimulate the second neuron. So what I'm going to see over here, that which ions are going to do that. If the ions are exciting, that means these changes are depolarization. I told you if it is going away, that is from the normal polarity, that is it is going dur, that means it is going away from the normal negative polarity, we call it as depolarization. And if it is going more towards the negative polarity, we call it as hyperpolarization, because normally the polarity is negative, we are going more into the negative, that's why we call it as hyperpolarization. Now remember that if the ions are causing depolarization, then I'm going to say that suppose there are some neurotransmitter which was released from here and this another neuron got stimulated, right? It got excited. And whatever changes are going to happen, that is going to happen in the different, that is second neuron, isn't it? This is going to happen in the after the synapse, that means in the second neuron. So whatever changes are going to happen, that is going to happen post-synaptically. So that's why we are going to call it as post or excitatory post-synaptic potentials. So excitatory post-synaptic potentials. And if we write it in the short form, it is going to be EPSPs. Okay. And same over here, if we talk in terms of hyperpolarization, then these are going to be in the negative. So if I release inhibitory neurotransmitter, let's say for example, I'll show you in the same color, then they will make the second neuron to go in the inhibition, and these changes are also seen post-synaptically, and that's why they are called as inhibitory post-synaptic potential. Inhibitory post-synaptic potentials, which are called as IPSPs, as easy as that. Okay, so if inhibitory neurotransmitter are released, inhibitory postsynaptic potential, excitatory are released, excitatory postsynaptic potential. So IPSP and EPSP, the short note comes usually. Okay, so what are the ions? Let's see. So there are two ions which can cause the excitation. We have seen that. And what are those ions? Sodium as well as calcium. Whenever they are more outside, whenever we open up their channel, what is going to happen? Their influx will occur, and their influx is going to bring the positivity inside the cell, which are responsible for EPSPs, right? And if we talk in terms of potassium, as soon as we are going to open those channels, it is going to cause potassium efflux, isn't it? And whenever we are going to open up the chloride channel, the chloride influx will occur. That means they are going to come inside, and both of them are going to create the IPSPs, isn't it? One of the example I'm going to give, because we don't have much of the time, so only one example I'll give about the GABA. Now remember, the GABA is the neurotransmitter which is released by the neurons, and depending on what type of receptor it is going to activate, it is going to open up the channels. Okay, so there are two types of major receptor. There are three also, but we are going to talk about two, that is GABA A and GABA B. Remember, GABA A will open up the chloride channels, GABA B will open up the potassium channels. The same changes are going to happen, right? Whenever they are going to open up the chloride channels, the chloride will move inside, right? So what is going to happen to the chloride? The influx will start, and it will create IPSP again. So whenever the patient is more anxious, it is having the anxiety attack, panic attacks, we give something known as, or psychiatric illnesses, we give something known as benzodiazepines. Okay, these are the drugs which calms the patient down via producing the IPSPs in his neurons. Especially the anxiety patient, the psychiatric disorder patient, we give the benzodiazepines. Okay, what about the potassium? As soon as you open up the potassium channels, what is going to happen? Again, the potassium efflux will start, right? And that efflux is helpful in the drugs also. We are going to use that information for our benefit. There is a drug which is known as baclofen. The muscle, usually what happens, especially when we talk about the skeletal muscle, sometimes the skeletal muscle go in the sustained contraction, right, or continuous spasmodic contraction. We want to relax those muscles, right? So we are going to give the drug which is known as baclofen, which is going to act as a muscle relaxant, and via acting the IPSPs, or via creating the IPSPs, we are going to stop the stimulation of that muscle, hence the muscle can relax. Okay, so benzodiazepine, baclofen, based on the IPSPs and EPSP, we are going to use our knowledge over there. Right, let's move on to the difference between local potential and action potential. See, action potential we have already learned, and whatever the diagram I have shown you over here, these potentials are not action potential, and that's why they are decaying. They're not showing any proper graph, right? Hyperpolarization and depolarization, spike potential. Nowhere I am mentioning the spike potential. Why? Because they are going to get generated in that area, but they won't propagate forward. Those changes will be present in that particular area, and they will have the decay over there itself, right? They won't propagate, they won't go forward. And that is the difference between action potential and local potential. Whatever local potentials are there, they're going to get produced there only. They won't get more of the fame, they won't go forward, right? So what should be the stimulus? The stimulus, if it is not reaching the threshold, the potential changes are going to happen, but those changes will remain in that area. Okay, because the action potential is required if you want to go forward. That means if you want to propagate those signals, we have to reach the threshold potential, isn't it? So stimulus is going to be, in the case of local potential, it is going to be subthreshold stimulus. In the case of production of action potential, it must be threshold or higher than the threshold, that is suprathreshold. In the case of local potential, there will be no propagation, but the propagation will happen in the action potential. What about the response? The response over here is graded response. What do you mean by graded? You can see over here in this diagram. If I give less stimulus, there is less response. If I give more stimulus, there will be more response. That is not going to happen in the action potential. Whatever threshold stimulus you give, threshold stimulus, submaximal stimulus, maximal stimulus, it is going to reach to the same level of spike potential. It is not going to show you the grades, different grades. No, that is not going to happen in the action potential, isn't it? So the response in the case of action potential is going to be all or none. Either it will give its 100%, or it is not going to give any response. There is no in between, right? So if you want to study, give your 100% concentration, do it with your 100% concentration, or just don't do it, right? So all or none law. What about the summation? Remember, the local potential, if you give in a particular time interval, so they can add up to it. Okay, so first stimulus is there, the second can add on to it, and the third can add on to it, right? But this is not going to be seen in the case of action potential. They cannot add because their own response is maximum. And remember, in the action potential, we do have refractility time also, and that's why, because of that property, the summation won't occur in the case of action potential, but it is going to be present in the case of the local potential. We have learned the types of summation in the last lecture itself. What about the stimulus or you can say the potential that is going to be produced, depolarizing or hyperpolarizing. Both the types will be seen in the graded potential. Just now we saw in the example. But remember, in the case of action potential, it is going to be always depolarizing. If you are giving the hyperpolarizing stimulus, the excitability will reduce. It won't increase. It won't give you any response. Okay. What about the decay or decrement? It is going to be seen in this case and not in the action potential. Action potential will propagate unless and until it reaches to the axon terminal. Okay. What about the site of genesis? The local potentials can produce anywhere, but the most common site is going to be dendrites or soma. Dendrites or soma. Right? And we know the site of genesis in the cases of motor, it is going to be either initial segment. In the cases of motor neuron, and in the cases of sensory, it is going to be nodes of Ranvier. And we remember via the mnemonic. Can you tell me the mnemonic? What was the mnemonic? Tell me the mnemonic of the sensory and motor, where the site of genesis occurs. Tell me the mnemonic, and then we will, till that time, I'm going to draw the action potential, which we have already discussed in the lectures. Right, so suppose this is the minus 70 MV, this is going to be minus 55 MV. Around plus 30 to 35 MV we reach the spike potential. How we are going to reach it? I'm going to give the stimulus, threshold stimulus, that is going to be at least 15 millivolt, right? It is going to reach up to the firing level. As soon as it reaches to the firing level, the sodium channels are going to get open up. Right, as soon as the sodium channel open up, the Hodgkin cycle will start. That is, opening of sodium causes more opening of more sodium channels. Right, they will call more sodium, and that is going to reach up to the spike potential. As soon as it is going to reach up to the spike potential, sodium channel will be inactivated and the potassium will be open up. So the potassium efflux will start. But I discussed that the potassium, K for Kachwa, they are slow to open, slow to close, and that's why what is going to happen over here, if they are slow to open, slow to close, even if they reach up to the RMP, they won't close very quickly, and that's why the cell go into the hyperpolarization. But after some time, it will come back to its normal RMP. So sodium influx you can write over here, right? So this is the action potential in the nerve, right? So why it is minus 55? Because it is the firing level, right? Don't want to get fired, you don't have to reach the spike potential. We have talked about the refractility also. There are two types of refractory periods are there. So from the starting point till the 1/3 of repolarization, and from 1/3 of repolarization till the time it reaches to the RMP back again. What I told you, that R to R is going to be RRP, right? R to R is going to be RRP, and absolute refractory period is going to be from starting to the 1/3 of repolarization. Refractory means no response. So there will be no response whatsoever is going to be there in the absolute refractory, while in the relative refractory it is going to be having or showing the response if the stimulus is more than the threshold, okay, or more than the beginner response. Refractory. Okay, now what is the significance of this refractility? First, understand there is a more refractory, absolute refractory period is present, more ARP is there in cardiac muscle, almost 100 times more. Remember, in the skeletal muscle it is 1 to 3 milliseconds, but in the cardiac muscle it can reach up to 180 to 200 milliseconds. I'm just talking about the ARP. Okay, so ARP is 180 to 200 milliseconds is in the cardiac muscle, while 1 to 3 seconds milliseconds is in the skeletal muscle, right? So in the skeletal muscle it is going to be 1 to 3 milliseconds, and in the cardiac muscle it is going to be much higher. Now understand what is going to happen. Because of this, the heart cannot be stimulated back again, so the heart can't be tetanized, right? And what about the RRP? If you give higher stimulus, can stimulate the heart muscle. That means supra-threshold stimulus, right? In the RRP itself, it can give another response. You can get second response abnormally before premature response, right? And if you are getting premature contraction, this will be called as premature ventricular contraction. Premature ventricular contraction, which is known as PVC, or it is also known as extrasystole. It is also known as extrasystole, and please remember, extrasystole compensatory pause, this is because of the RRP if you give any extra stimulus over there. And we know that the permeability of the sodium is going to start first and the potassium will be followed by it. Both of the channels will be open as soon as you give the stimulus, but as we know that the potassium is kachua, so that's why it takes more time to reach up to the highest permeability, right? And then it will fall, it will start to fall. So they can ask you, they can just remove these things over here. From here they're going to remove these and they're going to write X and Y. They will give you the same graph, just they are not going to write sodium and potassium. And they can ask you which graph is seen during the depolarization, or the permeability of the ions can be seen during depolarization. Then you are going to mark it as X graph. If they ask about repolarization, then you are going to mark it as Y graph, right? So I just wanted to show you the action potential over here. So see in the graph how the action potential is following. So as soon as the action potential continues into the nerve, what is going to happen? See, calcium channel is opened, isn't it? And the opening of calcium channel over here, that causes influx of the calcium, and because of that the vesicles got they release the neurotransmitter. This neurotransmitter, they will go and sit on these channels. See over here now, they are going to go and sit on this channel. What is going to happen? The doors of these channels, they were open, and as soon as these doors was they were open, what is going to happen? The sodium will start to enter. Why? Because these are the ligand gated sodium channel. And what is this? This is the sarcolemma, right? This is the muscle membrane which is shown over here, right? And those muscle membranes are going to get activated, and that's how the message from the nerve is going to transfer into the muscle. So this is the nerve, this red one is the muscle, okay? And the action potential comes in the nerve, open up the calcium channel, causes exocytosis of the neurotransmitter. Especially if we talk about skeletal muscle, it is going to be acetylcholine, which will sit on the receptor and activate the ligand gated sodium channel. And from here you can just see the gates are open now. Now the sodium start to move inside, right? And you can see the sodium coming inside, right? And that is going to cause the depolarization. As soon as it is going to hit the threshold, the action potential is going to get generated, and this will travel along the membrane of the skeletal muscle. That is nothing but the sarcolemma. That is nothing but the sarcolemma. Okay, you can see that there are going to be tubules which are going to be present on both sides of tubule. If I just zoom it in, you can see on the both sides of tubule there are green molecules. What are these? These are the sarcoplasmic reticulum, or these are also known as L tubules. Okay, and you can see that these looks like a T, right? And these tubules which are going through and throughout of the muscle, this is known as T tubule. So there are two types of tubules, T tubule and L tubule. Now I told you that the calcium was doing two things. Over here the calcium was doing what thing? It was causing the exocytosis, isn't it? It is going to cause that means it is important in the nerve also, and in the muscle what it was causing? See over here, in the muscle it was over here the action potential will be travel along this T tubule, right? As soon as it is going to travel along the T tubule, it is going to open up some channels in the muscle that we'll see just now, and it will cause the release of calcium. So you can see these molecules. What are these? These are calcium, and they are going to cause the contraction in the muscle cells, right? And these are the myosin fibers which are present in between, and these red ones are the actin. This start to slide over each other, and as soon as they slide over each other, that is nothing but the sliding filament theory, because it looks as if two filaments are sliding over each other, and the sliding filament theory was given by A.F. Huxley. There was a scientist known as Sir Andrew Fielding Huxley who gave this sliding filament theory. He saw first of all how the contraction of the skeletal muscle occurs. Okay, so I hope via these animations you can understand it in a better way, that how this is going to happen in the cells, right? So in the brief we can see that action potential, as soon as it is generated in the nerve, it is going to travel along the axon and it is going to hit the axon terminal. As soon as it is going to hit the axon terminal, what is going to happen? We just now saw that the calcium channels are present at the axon terminal, which is going to get open up, and as soon as the calcium channels are going to open up, what is going to happen? Obviously there is going to be exocytosis which is going to happen. As soon as the exocytosis happens, then this acetylcholine, they go and sit on this ligand gated sodium channels. The ligand gated sodium channels will open, the sodium entry will take place into the sarcolemma, and that will produce the action potential in the muscle cell also. And you can see over here, as soon as the calcium enters, the neurotransmitter has to go out, right? So it is heading outside. Okay, so this is the meme that can help you remember all these things. You can see over here, this is the diagram over here. So sarco means skeletal, lemma means membrane. Okay, so sarcolemma, that means the membrane of the skeletal muscle. You can see there are these pores available which are actually traveling through these muscles, and they are nothing but the T tubules. They see as T tubule, so that's why they are known as T tubule, right? Their shape looks like T, and that's why they are known as T tubule, or these are also known as terminal cisterns. And you can see that there are horizontal lines also, and these horizontal lines, they are nothing but the L tubules which are going to present on both the sides of these. You can see these lines over here. These are the L tubules which are going to be there. So that makes the triad. So what is the triad? One T tubule and two L tubules surrounding it, they are going to make a triad. So one T tubule plus two L tubules, they both combinedly, they are going to make a triad. Why I'm stressing so much about it? Because it is going to be coming as the long question on the excitation contraction coupling. Okay, so very important. I've shown you this GIF already. See carefully over here. We are going to cover this topic, and contraction we will see the next day tomorrow, right? So see over here what is going to happen. We have already discussed some steps over here, that the action potential will be this is the nerve, so action potential will hit the axon terminal, calcium channel will be open. As soon as the calcium channels are open, these red molecules, they are nothing but the acetylcholine molecules. They are going to sit onto the ligand-gated cationic channels or ligand-gated sodium channels. The sodium will be entering inside the cell. As soon as the adequate amount of sodium came into the cell, that will generate the depolarization and action potential. And the funda about the action potential is it is going to propagate. It is going to propagate. Now we are talking about the muscle, or this is known as motor end plate. It is going to propagate along the sarcolemma, that is the action potential is going to propagate along this sarcolemma. Till what point? There are some receptors which are present on the sarcolemma which are known as DHPR, dihydropyridine receptors, which are going to be present on the sarcolemma. They are going to get stimulated. Remember, these are receptors, they are not channels in the case of skeletal muscle, but they are channels in the case of cardiac muscle, right? What is the difference and how this is going to matter? We'll learn whenever we are going to see the differences. For now, just remember they are the receptors. DHPR receptors are there on the skeletal muscle. As soon as the action potential stimulate these receptor, you can see there is a mechanical connection of these receptors with the calcium channels which are present on the sarcoplasmic reticulum, which we call it as L-tubule. Isn't it? What is going to happen? You can see that as soon as these channels are stimulated, the RYR channel, it will cause the coiling of that spring-like structure, which is the physical or mechanical connection between DHPR and RYR. As soon as the spring is going to coil, the channel is going to open up, right? So this is the resting condition in which you can see that the RYR was closed. But as soon as it is going to get stimulated, what is going to happen? These calcium channels will be opened, and now the sarcoplasmic reticulum, which is the storehouse of calcium, it is going to start releasing the calcium. And as soon as the calcium come out of this sarcoplasmic reticulum into the myoplasm, that means as in the cell we do have cytoplasm, in the muscle we do have myoplasm. As soon as they are going to come into the myoplasm, there are filaments which are going to be present, that is actin and myosin, and they are ready to meet each other. And who make this possible? The calcium. As soon as the calcium will enter into the cytoplasm of the muscle, that is the myoplasm, the contraction will take place. Okay, so let's write these steps. EC coupling. First of all, what is the EC coupling? The excitation of the muscle membrane or motor end plate will be followed by contraction of the muscle after giving adequate stimulus. After giving adequate stimulus. So definitely it is going to produce the action potential in the muscle, which will be followed by the contraction in the muscle. Okay, and what are the steps that are present? First of all, the action potential, which will be coming from the nerve. So action potential in the nerve is going to cause opening of calcium channel, and these are opening of voltage gated. So these channels are voltage gated calcium channel. That means they are going to sense the voltage. They are going to sense the depolarizing changes that are going to happen in the axon terminal. They are going to cause exocytosis. The calcium entry will take place, and that will lead to exocytosis of neurotransmitters. Specifically, it is acetylcholine, which is going to go and bind to ligand gated cationic channels or sodium channels. Mainly sodium will enter, so I'm writing sodium channel over here, right? I'll continue that on the next page. That sodium channel, it is going to be carry forwarded in the sodium channel. What is going to happen due to that? That as soon as the sodium channels are going to get open, that will cause sodium entry, lead to depolarization of sarcolemma. This is also known as motor end plate. Motor means in the muscles, whatever is happening is it isn't happening in the muscle. So motor end plate, right? Now this depolarization will be carry forwarded to the tubules. Carry forwarded. The action potential will be carry forwarded if the stimulus is adequate towards the T tubule, unless it stimulates the DHPR, that is dihydropyridine receptors. Dihydropyridine receptors. Okay. Now remember, I'm saying stimulation of dihydropyridine receptor and not the opening, because the opening is going to happen in the cardiac muscle, not in the skeletal muscle. There is a slight difference in that. Okay. And that will lead to opening of RYR or ryanodine receptors on the sarcoplasmic reticulum. That is going to open up the calcium channel. These RYR are nothing but calcium channels on sarcoplasmic reticulum. That will lead to calcium entry in the myoplasm, and that ultimately leads to the contraction. That is going to lead to the contraction. The calcium entry is ultimately important. As soon as the calcium entry is going to happen, everything will fall into place. In the nerve, the action potential will be carried forwarded, the exocytosis will occur. So please remember, in the nerve muscle physiology, calcium has two roles. First is exocytosis, second is contraction. Okay, there are many roles of calcium, but in the nerve muscle physiology, these two are the major roles. Okay, what are the differences in the AC coupling of the cardiac muscle and the skeletal muscle? Please remember, again, the same thing is going to happen. Just I'm going to note down the difference over here. That first thing, the difference is over here the dyad is present and not the triad. That means only one T tubule and one L tubule is going to be present. One T tubule and one L tubule is going to be present. And remember, there is something known as CICR, calcium induce, calcium release. There is something known as calcium induce, calcium release is also present in this case, and that is your homework that you have to do and tell me tomorrow. Tomorrow we are going to meet same time, right? That is again 6 o'clock. And I'm going to revise this topic for you. If you do not get it, don't worry, we are going to anyhow discuss, but I want you to do this homework, right, and come back tomorrow. Okay, and calcium is going to bind to some channels, that is calcium is going to come through the channels and it is going to bind to troponin, which is going to cause again the sliding filament theory, which we'll be discussing tomorrow, again continuing tomorrow. So in the sliding filament, what is going to happen? There are some molecules. Just for now, remember that there are actin molecule and the myosin molecule. One is a thick filament, one is the thin filament, what is going to happen? Those thin filaments, they are going to slide onto the thick filament, okay? And the myosin is masculine. So please remember M for myosin, M for masculine. That means it is going to be a thick filament which is going to have head-like structure. You can see over here that there is a head-like structure which is going to be present, right? And there are different molecules which are present. So you can see, just for now, just remember, because anyhow we are going to discuss that. So see over here, there are 4 molecules that you have to remember. First 2 things that you need to remember is the actin, right? That is one of the filament. Second is myosin, another filament. I told you myosin is masculine, so it is going to be the thicker filament which is going to have head also. And actin is thinner, so it is going to slide on to the myosin, and that's how the muscle contraction is going to take place. But we do have some important protein molecules also. And what are those protein molecules? First is going to be the troponin, and second is going to be tropomyosin. Now remember about the troponin and tropomyosin, I'm going to show you one diagram over here. So see in this diagram what the actin and myosin they want to do. They want to meet with each other, but the tropomyosin is not allowing it to meet. That means for the sliding filament theory, we require to have this actin and myosin cross bridge formation, but the tropomyosin will be hindering it. Okay, not only that, there is another molecule I just now told you that is going to be troponin, right? So just for now remember that the troponin is the heterotrimeric protein. That means there are going to be trimeric. I told you 3 different types of molecules are going to be there. What are the 3? Troponin T is there, troponin I is there, and troponin C is there. TIC. So this is the troponin molecule, not tropomyosin, it is the troponin. Okay. Troponin T. What the troponin T will do? The troponin T is going to bind to the tropomyosin at resting phase. So that's why in the resting condition the muscle won't contract. Why? Because thankfully we have the tropomyosin and troponin T, right, which will inhibit the contraction. Then we do have troponin I. What the troponin I is going to do? It is going to inhibit the actin to bind with the myosin. So it is inhibit the cross-bridge cycling. Inhibit the cross-bridge cycling. And we do have troponin C, which is very important. Why? Because C for calcium. C for calcium, please remember that it is going to bind to the calcium. So as soon as the calcium will get released, just now we talked about the DHPR and RYR channel. As soon as the RYR channels, they are going to get open up, the calcium will be released from the RYR. It is going to come into the myoplasm. It will bind to this troponin C, right? So let's say the calcium is bound over here. Now what will happen? That this troponin I will be inactivated, and this troponin T, since it is having the connection with the tropomyosin, it is going to move that tropomyosin away from the active site of actin. There are specific sites where the myosin is going to bind to the actin. Okay, it cannot just bind to anywhere in that globular molecule. Okay, it has to bind to that specific site, which is covered by this pink filament you can see over here. So I'll just show you that this is the tropomyosin, right? And you can see that there are these dark blue color round shape structures onto which this is running. What are these dark points? They are nothing but the active site of actin, which should be bound to the myosin. The myosin only can bind to these sites of the actin, not anywhere else. For the binding of the active site of actin to the myosin, we have to remove the papaji of myosin from the way. right? Then only the actin and myosin can meet, right? So to remove the tropomyosin, we require calcium to bind to the troponin, this troponin C. As soon as it is going to bind, it will remove the tropomyosin away from the active site of actin. You can see over here that the pink molecule has slided away from the active site of actin. So these were the active site of actin. You can see the dark dots over here. Now they are free to bind to the myosin. There is no tropomyosin on the top of it, and that's why now, because of the calcium entry, it is possible that the calcium will bind to the troponin C, and the troponin C will remove the tropomyosin. As soon as it is going to remove the tropomyosin, what is going to happen? Definitely this active site of actin will be available for the binding of the myosin, and that will lead to contraction. Okay, and as soon as the calcium will be removed, let's say from the sarcoplasm or the myoplasm, what is going to happen? Definitely this troponin I will be activated again, right? And this troponin C will not longer be activated, and this troponin T won't be able to distract the tropomyosin away from the active sites of actin. And again, as soon as the calcium will go back to the sarcoplasmic reticulum, this condition will be reversed back again, so that the actin and myosin cross bridge cycling won't be able to occur, and that means the contraction will stop. So that's why I told you in the nerve muscle physiology, the calcium is very important. Whatever is happening, that is because of this calcium, which is very, very, very important, right? So before moving on forward, what I want you to tell is the applied aspect of this RYR. Now remember, the applied of the RYR, what is the applied aspect? That there are some condition in which this RYR is going to get mutated. That means it gets hypersensitized. And hypersensitized, that means there are some anesthetic agents such as succinylcholine, to which it is going to get via which it is going to get hyperactivated. If there is hyperactivation, let's write like that, of RYR, what is going to happen? More calcium will be released, from the sarcoplasmic reticulum, isn't it? If more calcium will be released from the sarcoplasmic reticulum, what is going to happen? Definitely more calcium will remove more tropomyosin, and that will lead to more cross bridges. And because of what is going to happen? Because of this, because of the more cross bridges cycling, whenever, remember, the contraction occurs, not only the ATP is used, but the heat is also generated. That heat will be released more and more, right? So more will be the contraction, and more heat will be released from the muscle. And when more heat is released, what is going to happen? Yes, please. There is a condition which is known as hyperthermia. Whenever we say that the temperature is going to increase, we call it as thermia for temperature, right? And this is the condition which is known as malignant hyperthermia. Malignant hyperthermia, which is going to be taking place, this is because of the hypersensitivity of the RYR. There is no particular cause of this. This is the genetic mutation which can be seen in some patient, and that's why we, first of all, whenever we are giving the this succinylcholine, this is the anesthetic agent, so we have to check for it whether it is not reacting too much. The patient is not reacting too much to it, and the temperature is stabilized. Otherwise, they are going to lead, or they are going to fall into the malignant hyperthermia, right, which is the condition which is going to be very, very dangerous for the patient itself, right? Tomorrow we are going to learn about the sarcomere, because we don't have much of the time, right? Let's complete this contraction, and then tomorrow we are going to learn about the EC coupling in the cardiac muscle, sarcomere, and then we are going to move on to the next thing. Okay, so first of all, I'll just complete the EC coupling today. So calcium got released, right? The calcium release, till that we learn calcium release from R by R or through R by R from sarcoplasmic reticulum. Isn't it? And that is going to bind to troponin C, that will displace the papagy of myosin, that is tropomyosin. We say the actin and myosin, they are like girlfriend and boyfriends, right? So they want to meet, but the papagy of myosin, they are not allowing it to meet. So we have to distract the papagy, that is tropomyosin. We have to displace the papagy of myosin, that is tropomyosin. Once the kebab mein se haddi is alag, different hai na, so what is going to happen? The active site of actin are free to bind to myosin, right? So they are going to bind on the myosin, right? So active site of actin, they are going to bind to the myosin, and as soon as the actin myosin they meet together, this is known as the cross bridge cycling. The cross bridge cycling will start, right? And that will lead to the sliding filament theory. Which will lead to contraction, that we are going to discuss tomorrow. Okay, so this is very, very important phenomena which is going to take place in the case of muscle, right? Let's solve the question. Tomorrow we are going to learn about the whole of the sarcomere. Sarcomere is the functional unit of the muscle, isn't it? So let's talk about some questions. There is one question which is more of the Ames pattern. So assertion, give me the answer very, very quickly. Assertion and reason is given over here, right? First assertion is given, that is in absolute refractory period, the nerve cannot be stimulated even with a strong stimulus. Is it true or false? Yes, tell me please. In the comments, tell me, is it true or false? Both assertion and reason statement, they are correct. The reason is the correct explanation for the assertion. What is the reason? Majority of the sodium channels are inactivated in the inactivated state during the early part of the refractory period. Identify the correct statement, right? So assertion is given that the ARP may, even if you give the strong stimulus, nothing will happen. And they have given the reason that the sodium channels are inactivated. Both are true. One is true, one is false. Tell me what it is, right? So both the assertion and reason are correct, but the reason is not the correct explanation, or it is the correct explanation. The assertion statement is incorrect, but the reason is correct. Both are incorrect. Okay, tell me what is the answer of this question in the comments. Sliding filament over thick filament. Yes, Ritesh, you're right. Tell me the answers of quickly so that we can finish the session of today. What do you think? ARP is refractory. I told you that the refractory means there will be no response whatsoever, isn't it? So no response, that means it is true that no matter how strong stimulus you give, there will be no response, absolutely no response, right? Like my brother, he doesn't study no matter how strong stimulus is given by my dad, है ना? So he is absolutely refractory. He become relatively refractory when the exams are near. Only that time he is relative refractory. He is still refractory. Okay, so absolute refractory period, that means it is true that no matter how strong is the stimulus, there will be no response. Okay, so that means this statement is correct. What about the reason? Majority of sodium channels are inactivated. That's true. That as soon as we fall in the ARP, what happens? That the as soon as we reach the spike potential, most of the channels are inactivated. I told you that is the reason behind the accommodation also, right? Why? Because they are time gated channels. So after some time they tend to get inactivated. There are two different doors. One is inactivated gate, one is activated gate. The inactivated gate is stubborn gate, right? That is a H gate of the sodium channel. No matter how strong stimulus you give, it is not able to open up, and that's why the sodium entry is not able to happen, and that's why this is absolute refractory period. They come out of the inactivation once the 1/3 of the repolarization is over, and that's why the ARP will be converted into RRP after 1/3 of the repolarization, isn't it? And that means both the assertion as well as the reason, they are correct, and the reason is the correct explanation for the assertion. So answer over here becomes A, option A. Let's move on to the next question. Guys, give me the answers quickly. I know there is some lag maybe, but give me the answer so that it will be, a bit of motivating for me also to discuss the question at the end, which are very, very important kind of a practice, right? Under physiological condition, what will be the resting membrane potential of the neurons? Tell me, what is the resting membrane potential of the neurons? We have discussed that in the today's class itself. Yes, please, I'm waiting for your answers, guys. Tell me, what was the answer? Yes, Ritesh, you are absolutely correct. What are the other students doing? Give the answers, bacho. Yes, you are correct that we have discussed about the neurons. The four things you have to remember at least: neurons, skeletal muscle, as well as cardiac muscle, which is more or less the same, having same action potential, this resting membrane potential, cardiac muscles, and then comes the smooth muscles. So in the neurons we have discussed minus 70 MV. In the skeletal and cardiac they have to produce force, so maximum minus 90 MV. And smooth muscle, it is around minus 50 MV, right? So yes, Ritesh, you're the only one who is answering. What happened to other students? Gajendra, Urvesh, Yugal, answer bacho. So option B is going to be the answer over here. And these four things you have to remember, because many a times they have been repeated again and again in all the entrance examination, not only that, in the university exams also, right? Let's move on to the next question. Which of the following ions have equilibrium potential close to the resting membrane potential? That means if they ask equal to the equilibrium potential of which ion, then the answer will be different. If they ask close to, then the answer will be different. Okay, on the verdict you have to change your answer. If they ask close to, that means whatever is maximally responsible for the RMP, you have to tell the answer for it. Yes, Ritesh, you are right. Smooth muscle mein it is minus 50. Tell me the answer of this question. If I write equal to, then the answer will change. If I write close to, the answer will change. Close to means I'm talking about that particular ion which is responsible for the resting membrane potential. So if I write close to, my answer should be, yes please, if I write close to, my answer should be the ion which is responsible for it and not the other ions. If I write equal to, then only I can write it as chloride. Then only I can write it as chloride. This question was asked and this is how they have explained it. Please remember that only if they have written equal to, then only you are going to answer it as chloride. If they have asked close to, then your answer is going to be potassium, because this is the one which is responsible for the RMP. when we talk mainly about the RMP of neuron or any other cell for that matter, remember at the resting time, who is having permeability? The potassium, right? So it is, if they ask close to, please remember, don't get confused. It is written correctly. The answer has given correctly in the question bank also, because in the question bank the same question was given, right? So answer over here is going to be potassium and potassium, because they have asked close to, right? Let's move on to the next question. What is going to be the answer of next question? We have just now discussed that the absolute refractory period, again there is, let's write duration of absolute refractory period. What happened to you, bacho? Why you are not giving the answers? Give the answers quickly. I was discussing the cardiac, the CVS, then you were giving the responses. You only asked me to choose the muscle physiology. As soon as I started that, there are less responses, you know. So, duration of ARP, there are two muscles that we are going to discuss. First of all, the skeletal muscle. I'm going to write the whole duration of, let's say, ARP I'm going to write first of all, and duration of action potential. The whole action potential, it is going to last for 2 to 5 milliseconds in the case of skeletal muscle, and in the case of cardiac muscle, in the skeletal muscle it is different. I'm just going to write ARP over here. Right? And the whole action potential. So, the ARP of that is the answer that you are going to give me. Yes, Ritesh, you are absolutely right. That is 1 to 3 milliseconds. Right? In case of these cardiac muscle, the action potential lasts for 200 to 400 millisecond, and the reason for it is plateau. We have discussed that already, that the plateau, that means whenever the potassium channel opens, suddenly the calcium channels also open in the cardiac muscle cell, and that's why there is no change in the this potential in the cardiac muscle for a long time, and that no change, that means the ARP is prolonged. There is no 1/3 repolarization which can reach early, and that's why the cardiac muscle is going to take more time. So please remember, it is going to be around 180 milliseconds. Okay, you can see the difference. There's a lot of difference between the ARP of the skeletal muscle and cardiac muscle, and that's why, what is the significance that we have learned? The significance is because of the long ARP, the heart muscle cannot be tetanized. The tetanization is not possible. That means tetany is what? Sustained contraction. No matter how strong stimulus you are going to give, no matter how quickly you are going to give, since there is a long ARP, the heart muscle cannot be tetanized. Okay, and the answer of this question is going to be option B. This question is repeated. Let's move on to the next question. Which of the following are seen in the T-tubules of the sarcotubular system of the skeletal muscle? Tell me the answer of this question. The T-tubule mein, which are the receptors which are going to be present? Are they ryanodine receptors? Are they acetylcholine receptors? Are they ligand-gated sodium channel? Or are they dihydropyridine receptors? What is the answer? The hint is, in the T-tubules, which receptors are present? Remember, in the sarcolemma, different receptors will be there, right? On the T-tubules, or in the T-tubules, different receptors will be there. On the sarcoplasmic reticulum, this receptors will be there. Okay? Tell me the answer for this. Should I even wait? So let's discuss about the ligand-gated sodium channel and acetylcholine receptor. These two were present on the sarcolemma or motor end plate. That means Where they are present? They are present on the membrane of the muscle, right? Not in the T-tubule. T-tubule is a whole different system, right? On the T-tubule, which channels will be there? On the T-tubules, the DHPR were there, right? And the ryanodine receptors, they were there on the sarcoplasmic reticulum. This DHPR channels are there on the T-tubule, right? So T sounds like D. So please remember, in the T-tubule, we are going to have DHPR receptors, right? So option D is going to be the answer over here. This is about the sarcomere. Tomorrow we are going to discuss about the sarcomere, right? So I hope you understood the topic that we have discussed today, right? Ritesh, you have given the answer. I think there is some lag, which is because of which we are going to have this difference in the timing, right? So these are the questions you have to write for the prof. These are the questions which are going to come for the prof. So give it a shot that if suppose this question comes, what answers you are going to write. So define the excitation contraction coupling and name the scientist who described the sliding filament theory. So just before going, I'll mention the name of the scientist, that is Sir A.F. Huxley. Remember, he was the scientist who got the Nobel Prize in around 1957, right, for the sliding filament theory, which is very heterotrimeric, right? So 3 different subunits having 3 different roles that you have to explain in this. Tropomyosin, Papa G of myosin, which are going to come in between, right, and which is going to hamper the contraction. Then comes the calcium. Role of calcium you are going to tell. In the skeletal muscle contraction only they have asked. So in the muscle you have to tell that. Then mechanism of excitation contraction coupling. So in the mechanism, you, depending on the marks, you have to define it also and explain the mechanism with the help of simple diagram. Okay. Then same in the cardiac muscle and skeletal muscle, right? And then the outline of ATP cross-bridge cycling, we can discuss that tomorrow. Relationship between the action potential and the contractile response. Okay. So all these questions you have to discuss about these questions, that if this question will come, what you're going to write. Okay. So we are just discussing the important topics over here, and in the next week we are just going to go through what are the important topics that I'm going to tell you in the next week. Okay, rather than taking your topics, because then your responses will be nil, hai na? And I'll be teaching to the camera. There are only few students who are replying me and making me feel alive, isn't it? So this is the message. I felt it is very wonderful. With that message, I want you to move ahead in your life, and I want to take your leave. That is, when we choose to trust the journey and embrace love and joy, we are free to fly. So embrace the journey, whatever is happening in the journey. Remember, this is the phase of the life, it's not the life. Even if you fail right now, don't worry about it, right? Go forward. Take whatever challenges are coming throughout your way, right? Don't get demotivated. No matter how many times you fall, get back again on your toes and prepare more than the last time, and keep on moving ahead in your life, right? No matter there are heartbreaking news that we are getting throughout the India, throughout the personal messages and call. Yes, my job over here is to console you, but again you have to go through that phase. I can just help you out, but then you have to find the courage to move on, and that is the most important thing. It is just a phase. Remember, after like 4 or 5 years you won't even remember this phase, right? Bad things happen with everyone, but the ones who just get over it, they are going to win the battle. So have the courage and get over the things that will make the discouragement in your life, and just move on. And that is all from my side. I hope you like the session. Thank you very much. For today, that is all from my side. Bye Ritesh. Bye guys.